We thought we knew where we were. For thousands of years, humans looked up at a river of stars stretching across the night sky and called it everything. The Milky Way, our galaxy, the universe itself, a single island of light surrounded by eternal darkness. We were not just wrong. We were off by a factor of 2 trillion. In 1929, Edwin Hubble aimed a telescope at a faint smudge in the constellation Andromeda and discovered something that should have been impossible. That smudge was not a cloud of gas. It was not a nearby star system. It was an entire galaxy, sitting more than 2 million light-years away, filled with hundreds of billions of stars we had mistaken for a wisp of nothing. And it was just the beginning. Because once Hubble opened that door, the universe did not stop revealing itself. It kept going, and the more we looked, the more we found, until the number became so large it lost all meaning. 2 trillion galaxies. That is the current estimate for what exists in the observable universe alone. Not 2 trillion stars, 2 trillion galaxies. Each one a system containing billions or even hundreds of billions of suns. Each one separated by distances so vast that light itself takes billions of years to cross the gap. And here is the part that should keep you awake at night. We can only see a fraction of what is actually out there. The rest is hidden behind a veil we may never pull back, held together by forces we cannot see, shaped by substances that make up 95% of reality and remain completely invisible to every instrument we have ever built. So how did we go from thinking we were everything to realizing we are almost nothing? How do you count something you can barely see? And what does it mean to exist in an ocean of light this impossibly large? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We used to think the universe was small. Not just small in the way you might call your hometown small, but truly, comprehensively, almost insultingly limited. For most of human history, the entire cosmos fit inside a single neighborhood, our neighborhood, the Milky Way. That band of light stretched across the night sky, the one you can still see from dark places far from city lights. That wasn't just part of the universe, it was the universe. Everything else, every star, every glowing smudge, every patch of fuzzy light visible through the best telescopes humanity could build, all of it was assumed to belong to this one enormous island of stars we happen to call home. There was nothing beyond it. No distant shores, no other islands, no vast ocean of space filled with countless other worlds. Just us. One galaxy, one universe, the end. This wasn't ignorance. This was the best science available. The smartest people alive looked through the most powerful instruments ever constructed and saw exactly what you'd expect to see if the Milky Way really was everything. Stars, lots of them, more than anyone could count, and scattered between them, fuzzy patches of light that telescopes could resolve but couldn't quite explain. Some of these patches were clearly inside the Milky Way, glowing clouds of gas lit up by nearby stars. Others were harder to pin down. They had structure. They had spiral arms. They looked almost like miniature versions of the Milky Way itself, which was strange but not necessarily revolutionary. Plenty of astronomers in the late 1800s and early 1900s simply assumed these spiral nebulae, as they were called, were either gas clouds in the process of forming stars, or perhaps distant, unresolved clusters sitting somewhere on the far side of our galaxy. Big, sure. Distant, maybe. but still part of the same cosmic neighborhood. The alternative was too strange to take seriously. A few voices, going all the way back to the philosopher Immanuel Kant in the 1700s, had suggested that some of these nebulae might actually be island universes. Entire galaxies in their own right, sitting so far away that even their combined light from billions of stars appeared as nothing more than a faint smudge. The idea had a certain poetic appeal. It also had no evidence. Telescopes of the era couldn't resolve individual stars in these nebulae. They couldn't measure distances. They couldn't prove anything one way or the other. So the conservative position, the one that didn't require rewriting the entire scale of the cosmos, was that the Milky Way was it. One galaxy, one universe. Case closed. Then in 1912, a quiet astronomer named Vesto Slipher, working at Lowell Observatory in Arizona, did something no one had done before. He pointed a spectrograph at the Andromeda Nebula, one of the brightest spiral nebulae visible from Earth, and measured how its light was shifted. Spectrographs split light into its component wavelengths the way a prism splits sunlight into a rainbow. By looking at where the dark absorption lines fall in that spectrum, lines caused by specific elements absorbing specific colors of light, you can tell whether an object is moving toward you or away from you. If it's moving away, the lines shift toward the red end of the spectrum. If it's coming closer, they shift toward blue. This is the Doppler effect, the same reason a train whistle sounds higher as it approaches and lower as it recedes, except with light. Slipher found that Andromeda was moving fast. It was approaching Earth at about 300 kilometers per second, which in cosmic terms is a respectably high speed. But here's the thing. Over the next few years, Slipher measured the spectra of more spiral nebula, and nearly all of them were moving away from us, not just drifting, fleeing. Some of them were receding at speeds upward of 1,000 kilometers per second. That was a problem. Objects inside the Milky Way don't move that fast. Stars in our galaxy orbit the galactic center at a couple hundred kilometers per second, give or take. To see something moving at 1,000 kilometers per second and still be gravitationally bound to the Milky Way would require a galaxy far more massive than anyone believed possible. The speeds Slipher was measuring were escape velocities, the kind of speeds you'd expect from objects that weren't bound to our galaxy at all, objects that were in fact somewhere else entirely. Slipher published his results. A few people noticed, most didn't. The data was strange, sure, but it wasn't conclusive. Maybe these nebula were being flung out of the Milky Way by some unknown mechanism. Maybe they were remnants of some ancient cosmic event. Maybe the measurements were wrong, the conservative position held. The Milky Way was still everything until 1923. That year, Edwin Hubble, a young astronomer working at the Mount Wilson Observatory in California, gained regular access to the 100-inch Hooker telescope, at the time the largest and most powerful telescope on Earth. He aimed it at the Andromeda Nebula and started taking long-exposure photographs, night after night, building up enough light to see details no one had ever seen before. And in those images, he found something that changed everything. Stars, individual stars, not fuzzy patches, not unresolved blobs of light, actual pinpoint stars sitting inside the spiral arms of Andromeda. And some of those stars were special. Hubble identified Cepheid variables. These are stars that pulse. They brighten and dim on a regular schedule, sometimes over days, sometimes over weeks, with a rhythm as steady as a heartbeat. And here's the key, the period of that pulse, how long it takes to go from bright to dim and back again, is directly related to how luminous the star actually is. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This relationship had been discovered a decade earlier by Henrietta Leavitt, an astronomer at Harvard who studied Cepheids in the small Magellanic Cloud. Her work gave astronomers a ruler. If you could measure how fast a Cepheid pulsed, you knew how bright it truly was. And if you knew how bright it truly was, you could compare that to how bright it appeared from Earth and calculate exactly how far away it sat. It was the first reliable cosmic distance measurement that didn't rely on parallax, the slight shift in a star's position as Earth orbits the Sun, which only works for nearby stars. Hubble measured the periods of the Cepheids in Andromeda. He calculated their true luminosities. He compared those to their observed brightness, and he did the math. The result was clear. Andromeda was sitting roughly 1 million light-years away. That number was wrong, as it turned out. Later refinements to the Cepheid calibration showed that Hubble had underestimated the distance. The modern value is closer to 2.5 million light-years, but the error didn't matter. Even at 1 million light-years, Andromeda was sitting far, far outside the Milky Way. The Milky Way itself, by the best estimates of the time, was maybe 100,000 light-years across. Andromeda was 10 times farther than that. It wasn't a gas cloud, it wasn't an unresolved star cluster, it was an entirely separate galaxy. An island universe sitting in the void, completely independent of our own. Hubble sent his results to Harlow Shapley, a prominent astronomer at Harvard who had spent years arguing that the Milky Way was enormous, far larger than earlier estimates suggested, and that the spiral nebulae were probably just outlying parts of it. When Shapley read Hubble's letter, he reportedly said, "Here is the letter that destroyed my universe." That's not hyperbole. Shapley had built his career on a particular vision of the cosmos. A big Milky Way, yes, but still one galaxy, still one universe. Hubble's Cepheids didn't just challenge that vision, they dismantled it. Andromeda was out there. And if Andromeda was out there, then so were all the other spiral nebulae. The universe wasn't a single island, it was an ocean. The shift in scale was dizzying. Imagine spending your entire life believing you live on the only continent. Then one day someone sails over the horizon and comes back with proof that there are thousands of other continents, each one just as large, each one just as real, scattered across an ocean so vast you'll never see most of them. That's what Hubble did to cosmology. He didn't just add a little more space to the map. He shattered the map entirely and replaced it with something incomprehensibly larger, and he wasn't finished. Once you know how far away galaxies are, you can start asking other questions, like, are they moving, and if so, how fast? Hubble already had Slipher's redshift data. Slipher had measured the velocities, Hubble had the distances. Put the two together and you get something extraordinary. The farther away a galaxy sits, the faster it's moving away from us. Not randomly, not chaotically. There's a relationship, a proportionality. Double the distance, double the velocity. This became known as Hubble's law, and it was the observational foundation for one of the most important ideas in modern science. The universe is expanding. Think about what that means. Every galaxy we can see, with a few exceptions like Andromeda that are close enough to be pulled toward us by gravity, is moving away from us, and the ones that are farther away are moving faster. That's not because we're at the center of some cosmic explosion. It's because space itself is expanding, carrying galaxies along with it, like raisins in a rising loaf of bread. If you rewind that expansion, running the clock backward, everything gets closer together. Keep going, and eventually everything was in the same place, a single point. Infinitely dense, infinitely hot, the beginning, the Big Bang. Hubble's law didn't prove the Big Bang, Not immediately, but it gave cosmologists the first direct observational evidence that the universe had a history, that it hadn't always looked the way it does now, that it was evolving. Hubble himself was careful about pushing the cosmological interpretation too far. He was an observer, not a theorist, and he knew that drawing grand conclusions from a handful of data points was risky. But the implications were hard to ignore. If galaxies are all moving away from each other, and if the relationship between distance and velocity holds across the entire observable universe, then the cosmos isn't static, it's dynamic, it's changing. And if it's changing now, it must have been different in the past. That insight reshaped everything. The discovery also did something else. It shrank us. Before Hubble, humanity could at least claim to live in the only galaxy. We were still cosmically insignificant in terms of our size, sure, but at least we had the whole universe to ourselves. After Hubble, we were just one planet, orbiting one star, in one galaxy, in a universe filled with billions of others. The philosophical impact was immediate. If there are that many galaxies, and if each galaxy contains hundreds of billions of stars, then the odds that we're alone, that Earth is the only place where life has ever emerged, start to look absurdly small. Hubble didn't discover alien civilizations. He didn't find evidence of life beyond Earth, but he made the question unavoidable. In a universe this large, this populated with stars and galaxies, how could we possibly be the only ones? There's a detail in the story that doesn't get talked about enough. Hubble's distance estimate for Andromeda was wrong, badly wrong. He was off by more than a factor of 2. And the reason he was wrong is that there are actually 2 types of Cepheid variables, and he didn't know it at the time. One type is intrinsically brighter than the other. Hubble used the wrong calibration, which made Andromeda look closer than it really was. That mistake was corrected in the 1950s by astronomer Walter Baade, who realized the error and recalculated the distances to nearby galaxies, effectively doubling the scale of the universe overnight. But here's the thing, even with the wrong number, Hubble's conclusion was correct. Andromeda was outside the Milky Way. It was a separate galaxy. The exact distance didn't change that. The philosophical shift had already happened. The universe had already expanded in humanity's collective imagination. Fixing the numbers just made it bigger. What Hubble proved in 1923 wasn't subtle. It wasn't a tweak to an existing model. It was a complete inversion of the cosmological order. The Milky Way went from being everything to being one tiny piece of a vastly larger structure. And that structure, as it turned out, was only the beginning. Because once astronomers accepted that there were other galaxies, the next question became obvious. How many? How far do they go? Is there an edge? And what lies beyond it? Those questions took decades to answer. They required bigger telescopes, better detectors, space-based observatories that could see wavelengths of light blocked by Earth's atmosphere. But the door Hubble opened in 1923 never closed. Every new instrument, every deeper survey, every more sensitive camera pointed at the sky has revealed the same thing. More galaxies, always more galaxies, fainter, farther, older, stranger. The universe refused to run out of them. Standing in that moment in 1923, staring at a photographic plate showing individual stars in Andromeda, Hubble couldn't have known what was coming. He couldn't have predicted the deep field images that would arrive 70 years later, showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. He couldn't have imagined the James Webb Space Telescope peering back to within a few 100 million years of the Big Bang and finding fully formed galaxies already shining in the infant universe. But he opened the door. He proved that the cosmos was larger than anyone had dared to believe. And in doing so, he handed humanity a gift and a burden. The gift was a universe of infinite possibility. The burden was the knowledge that we would never, ever see most of it. Knowing that other galaxies exist is one thing, seeing them is another, and seeing them as they truly are, scattered across distances so vast that their light has been traveling for most of the history of the universe, that requires something extraordinary. Something that didn't exist until the last few decades of the 20th century. It required sending a telescope into space. For all of human history, astronomy was done from the ground. You built the biggest mirror or lens you could afford, you pointed it at the sky, and you dealt with whatever the atmosphere decided to show you. And the atmosphere, it turns out, is not a cooperative partner. It bends light. It blurs images. It absorbs huge chunks of the electromagnetic spectrum before they ever reach the ground. Ultraviolet light, most infrared, X-rays, all of it gets filtered out by layers of air that are very good at keeping us alive and very bad at letting us see the universe clearly. Ground-based telescopes can do remarkable things, but they're always working through a veil. The idea of putting a telescope in orbit where it could see without that interference had been kicking around since the 1940s. It took until 1990 to actually do it. The Hubble Space Telescope launched aboard the Space Shuttle Discovery on April 24, 1990, carrying a 2.4-meter mirror and a suite of instruments designed to observe everything from ultraviolet to near-infrared. It was supposed to revolutionize astronomy. It did, just not right away. The first images Hubble sent back were blurry. Not a little blurry. Catastrophically blurry. Engineers quickly diagnosed the problem. The mirror had been ground to the wrong shape. The error was tiny, less than 1/50th the thickness of a human hair, but at the scale Hubble was designed to operate, that was enough to ruin everything. The telescope that was supposed to peer deeper into space than any instrument in history couldn't focus. NASA's reputation took a beating. Late-night talk show hosts had a field day. The Hubble Space Telescope became a punchline. Then in December 1993, NASA launched a repair mission. Astronauts aboard the Space Shuttle Endeavour spent 10 days installing corrective optics, essentially giving Hubble a pair of glasses. When the first post-repair images came down, the difference was immediate, sharp, clear, perfect. Hubble could finally see, and once it could see, astronomers started asking what they should point it at. One of the strangest proposals came from the telescope's director, Robert Williams. He wanted to aim Hubble at nothing, not at a nearby galaxy, not at a known cluster of stars, not at anything that had ever been catalogued or studied. He wanted to pick a patch of sky so dark, so empty, so devoid of obvious targets that no astronomer in their right mind would waste precious telescope time looking at it. Then he wanted to stare at that patch for 10 straight days. The idea sounded insane. Hubble's observing time was the most valuable scientific resource in the world. Every astronomer on the planet wanted a piece of it. Proposals were carefully vetted, prioritized, fought over. Time on Hubble was measured in minutes, and here was Williams suggesting they burn more than 200 hours on a blank patch of sky with no guarantee they'd see anything interesting. Most of the advisory committees thought it was a waste. Williams did it anyway. He had the authority as director to allocate a chunk of discretionary time, and he used it. In December 1995, Hubble turned toward a tiny region in the constellation Ursa Major, just above the bowl of the Big Dipper, and started collecting light. The field was absurdly small, 2.6 arc-minutes across. That's about 1/24th of the diameter of the full moon. If you held a grain of sand at arm's length, It would cover roughly the same amount of sky. From the ground, that patch looked empty. A few stars maybe, nothing else, just black. But Hubble didn't look for a few minutes. It looked for 10 days, and it didn't just take one picture. It took 342 separate exposures through different filters, capturing light across ultraviolet, visible, and near-infrared wavelengths. Then computers stacked all those images together, aligning them pixel by pixel, building up signal while averaging out noise. The final result was a composite image representing more than 1 million seconds of total exposure time. When the Hubble Deep Field was released to the public in January 1996, it broke astronomy. That empty patch of sky wasn't empty, it was full, absolutely packed with galaxies. The first counts put the number at around 1,500. Later analysis pushed it closer to 3,000. Almost every blob of light in the image, aside from maybe 20 foreground stars sitting inside our own Milky Way, was a galaxy. Some were nearby, cosmically speaking, sitting a few 100 million light-years away. Others were so distant their light had been traveling for more than 12 billion years. 12 billion. The universe itself is only about 13.8 billion years old. Hubble was seeing galaxies that had formed when the cosmos was still in its infancy, less than 2 billion years after the Big Bang. This is where the idea of looking back in time stops being a metaphor and becomes literal. Light travels fast, but space is big, really big. When you look at the sun, you're seeing it as it was 8 minutes ago, because that's how long it takes light to cross the 93 million miles between the sun and Earth. Look at the nearest star beyond the sun, Proxima Centauri, and you're seeing it as it was 4 years ago. Look at the Andromeda Galaxy, and you're seeing it as it was 2.5 million years ago. The light hitting your eyes right now left Andromeda before humans existed, before our genus existed, before most of the species we recognize as human ancestors had even evolved. Now, extend that principle across billions of light years. The galaxies in the Hubble Deep Field aren't just far away. They're far in the past. The most distant objects in that image are showing us what the universe looked like when it was young. Not theoretically young, actually young. Those galaxies, as they appear in the Hubble Deep Field, don't look like that anymore. They've had 12 billion years to evolve, to merge with other galaxies, to form new stars, to change. Some of them probably don't exist as independent objects anymore. They've been swallowed by larger galaxies or torn apart by gravitational interactions. The light we're seeing is a fossil, a snapshot of something that happened so long ago that entire galaxies have lived and died in the time it took that light to reach us. Think about what that means for understanding cosmic history. Astronomers can't watch a single galaxy evolve over billions of years. Human lifetimes are too short. Civilizations are too short, but they can look at galaxies at different distances, which correspond to different moments in time, and piece together the story. The Hubble Deep Field gave them a timeline. Nearby galaxies, the ones that are relatively close and whose light left them recently, show what mature galaxies look like. Smooth, well-organized, full of old red stars in some cases, or still forming stars in others, but clearly settled into stable structures. The distant galaxies, the ones whose light has been traveling for 10 or 12 billion years, look different, smaller, irregular, chaotic, clumpy. These are galaxies in the process of forming, still pulling themselves together out of clouds of gas, still figuring out how to be galaxies. The Hubble Deep Field didn't just show astronomers what the early universe looked like, it gave them a laboratory. They could count how many galaxies existed at different epochs. They could measure their sizes, their brightness, their colors. They could estimate how fast stars were forming inside them. They could watch, in a statistical sense, as the universe grew up. The data that came out of that one 10-day observation triggered hundreds of follow-up studies. Papers are still being published based on Hubble Deep Field data decades later. William's gamble paid off so spectacularly that NASA did it again. In 2004, Hubble aimed at an even smaller patch of sky in the constellation Fornax and stared for even longer. This time, the exposure ran for about 1 million seconds, spread over 4 months. The resulting image, called the Hubble Ultra Deep Field, went deeper than the original. It captured light from galaxies sitting at redshifts up to around 8 or 9, meaning their light had been traveling for over 13 billion years. The universe in those images was less than 1 billion years old. Some of the galaxies in the ultra-deep field are among the most distant objects ever observed in visible light, and there are about 10,000 of them. 10,000 galaxies in a patch of sky you could cover with a pinhead held at arm's length. Let that settle for a second. 10,000 galaxies in one tiny corner of the sky. The entire sky contains about 41,000 square degrees. The Hubble Ultra Deep Field covers about 11 square arc-minutes, which is about 3/millionths of 1 square degree. Scale that up. If the rest of the sky is even remotely similar in galaxy density to what Hubble saw in that field, and there's no reason to think it isn't, then the observable universe contains somewhere in the ballpark of 200 billion galaxies, maybe more. And each one of those galaxies contains hundreds of billions of stars. The math gets uncomfortable fast. But Hubble had limits. It could see far, but not far enough. The problem wasn't the mirror. The problem was wavelength. As the universe expands, light traveling through it gets stretched. This is redshift, the same effect Edwin Hubble used to discover that galaxies are moving away from us. The farther away an object is, the more its light has been stretched, shifting from shorter wavelengths, blue and ultraviolet, to longer wavelengths, red and infrared. By the time light from the most distant galaxies in the early universe reaches us, it's been stretched so much that it's no longer visible to the human eye. It arrives in the infrared, a part of the spectrum Hubble's instruments could detect, but not with great sensitivity. To see the very first galaxies, the ones that formed in the first few 100 million years after the Big Bang, you need a telescope designed specifically to observe in the infrared. You need something bigger, colder, and more sensitive than Hubble. You need the James Webb Space Telescope. Webb launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. It didn't go into orbit around Earth. It traveled to a point in space called the second Lagrange point, about 1 million miles away, where the gravitational pull of the Earth and the Sun balance out. From there, Webb could keep its massive sun shield pointed toward the Sun, Earth, and Moon simultaneously, blocking their heat and light, and keeping its instruments at temperatures cold enough to detect faint infrared signals from the edge of the universe. The mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's, giving it more than 6 times the light collecting area. And every single instrument on board is optimized for infrared. The first deep field image from Webb was released in July 2022. It showed a galaxy cluster called SMACS 0723 as it appeared 4.6 billion years ago. That's not particularly early in cosmic terms, but the cluster's gravity acted as a lens, bending and magnifying light from even more distant galaxies sitting behind it. Some of the galaxies visible in that image are more than 13 billion light-years away. Their light left them when the universe was less than 1 billion years old, and they're not faint smudges, they're sharp, detailed, clearly resolved structures. Spiral arms, star-forming regions, dust lanes. Webb can see features in these galaxies that Hubble could barely detect. Then Webb started doing targeted deep observations of its own, and the results were strange. Astronomers expected to find galaxies in the early universe. That wasn't the surprise. The surprise was how many there were, how bright they were, and how mature some of them looked. Standard models of galaxy formation predicted that the first galaxies would be small, dim, chaotic, proto-galaxies still in the process of assembling. Instead, Webb found massive galaxies, some weighing billions of times the mass of the Sun, sitting comfortably at redshifts of 10, 12, even 14. That corresponds to a time when the universe was only a few 100 million years old. According to the models, there shouldn't have been enough time for galaxies that large to form. Stars take time to ignite. Gas clouds take time to collapse. Dark matter halos take time to pull matter together. The early universe should have been messy, unformed, primitive. Webb showed otherwise. One galaxy in particular, spotted at a redshift of around 14, appeared to contain stars that were already somewhat evolved. Not the very first generation of stars, which should be composed purely of hydrogen and helium, but stars with heavier elements in their spectra. That means earlier generations of stars had already formed, lived their lives, exploded, and seeded the surrounding gas with carbon, oxygen, and other elements. All of that had to happen in less than 300 million years. The timeline is tight, uncomfortably tight. It's not impossible, but it forces astronomers to reconsider how quickly galaxies can assemble in the early universe. The other surprise was how common these early galaxies seemed to be. Hubble could detect a few candidates at extreme distances, but they were rare, sitting right at the edge of detectability. Webb sees them everywhere. Almost every deep field image Webb has taken contains galaxies at redshifts above 10. They're not anomalies, they're not flukes, they're a normal part of the early universe. That changes the math on how many galaxies formed in the first billion years after the Big Bang. It might also change our understanding of the role supermassive black holes played in early galaxy evolution, because several of these early galaxies show signs of harboring active black holes at their centers, something else that shouldn't have had time to grow that large that fast. There's a philosophical weight to these images that's easy to miss if you just look at them as pretty pictures. Every galaxy in a deep field, whether it's Hubble's or Webb's, is a place, an actual location in space containing billions or trillions of stars, many of which probably have planets, some of which might be capable of supporting life. And the light reaching us from those galaxies is ancient. It left its source billions of years ago. If there were civilizations on planets orbiting stars in those galaxies at the moment that light was emitted, they're long gone now. Their stars have aged, their galaxies have changed. In some cases, their galaxies have collided with others and merged into entirely new structures. We're not seeing those galaxies as they are, we're seeing ghosts. And here's the part that really twists the knife. They're seeing us as ghosts too. If someone in one of those distant galaxies happened to point a telescope toward the Milky Way right now, they wouldn't see us. They'd see the Milky Way as it was billions of years ago, long before the Sun formed, long before the solar system existed, long before Earth had cooled enough to have liquid water on its surface. They'd be looking at a galaxy full of stars that are almost entirely different from the stars we see when we look up at night. Our sun wouldn't be there, we wouldn't be there. The light carrying information about our existence hasn't reached them yet. It won't for billions of years. And by the time it does, assuming anyone is still around to see it, we'll be as ancient to them as those early galaxies are to us. The deep fields don't just expand the universe spatially, they expand it temporally. They turn astronomy into archaeology. Every observation at high redshift is an excavation, digging deeper into the past, uncovering layers of cosmic history that would otherwise remain hidden. And the deeper we dig, the stranger it gets. Hubble showed us that the early universe was full of galaxies. Webb is showing us that those galaxies were more complex, more varied, more mature than we thought possible. That's not a comfortable finding if you're a cosmologist trying to build models that explain how everything came to be. It means the models need work. It means there are processes we don't fully understand. It means the universe is still capable of surprising us. And it means we're not done looking. The deep fields we have now, stunning as they are just the beginning. Webb has only been operational for a few years. It's going to keep staring at the sky, finding fainter galaxies, pushing further back in time. At some point, it will hit a wall. There's a moment in cosmic history, about 380,000 years after the Big Bang, before which the universe was opaque. No stars had formed yet. No galaxies existed. The cosmos was just a hot, dense fog of hydrogen and helium, glowing uniformly in every direction. That glow is still visible today as the cosmic microwave background, the faint radio hiss left over from the Big Bang itself. Webb can't see past that. No telescope can. But between that wall and now, between the moment the first stars ignited and the present day, there are 13.8 billion years of history waiting to be explored. And every time we point a telescope at a new patch of sky and let it soak up light for days or weeks or months, we pull more of that history into focus. The galaxies are out there, billions of them, trillions maybe. And the only way we'll ever know how many, the only way we'll ever see what they looked like in their youth, in their prime, in their old age, is to keep looking. The deep fields proved that the universe is willing to reveal its secrets if we're patient enough to wait for the light to arrive. Looking at thousands of galaxies in the Hubble Deep Field is one thing. Counting all of them is another problem entirely. Because here's the uncomfortable truth. We can't. Not directly. Not even close. The universe is too big, the galaxies too numerous, and the limits of our telescopes too severe for us to sit down with a clicker and tally them up one by one. And yet, astronomers will tell you with a straight face that the observable universe contains somewhere in the neighborhood of 2 trillion galaxies. Not hundreds of billions, trillions. 2 million galaxies scattered across space, each one a separate island containing anywhere from a few million to several trillion stars. That's the number floating around in the scientific literature right now. And the question you should be asking is how anyone could possibly know that. Because we've only looked at a few tiny patches of sky in any real detail. We've taken maybe a handful of deep field images covering areas smaller than grains of sand held at arm's length. The rest of the sky remains largely unexplored at those depths. So how do you go from seeing a few thousand galaxies in a couple of narrow fields to claiming there are 2 trillion galaxies in total? The answer involves a lot of math, a lot of assumptions, and a lot of very careful guessing. But it's not wild guessing. It's educated, methodical, peer-reviewed guessing, the kind that holds up under scrutiny most of the time. Let's start with what we actually know. The Hubble Deep Field, that first groundbreaking 10-day exposure released in 1996, showed about 3,000 galaxies. Later refinements of the data pushed that number a bit higher, but 3,000 is a reasonable working figure. The field itself covered roughly 2.6 arc-minutes, which translates to about 1/24 millionth of the entire sky. If you assume, and this is a big assumption but a reasonable one, that the rest of the sky looks statistically similar to that patch, you can scale up. Multiply 3,000 galaxies by 24 million and you get 72 billion galaxies. That was the early estimate. 70 to 80 billion galaxies in the observable universe, give or take. It was a staggering number at the time. It also turned out to be way too low. The problem wasn't the math. The problem was what Hubble couldn't see. Telescopes have limits. They can only detect objects above a certain brightness threshold. Anything fainter than that threshold just disappears into the background noise. And the Hubble Deep Field, as deep as it was, still had a cutoff. There were galaxies sitting in that same patch of sky that were simply too faint for Hubble to pick up. Small galaxies, distant galaxies, galaxies whose light had been stretched so far into the infrared by the expansion of the universe that Hubble's visible light cameras couldn't register them. Those galaxies were there. Hubble just couldn't see them. And if Hubble couldn't see them in the deep field, it couldn't see them anywhere, which meant the 70 billion number was incomplete. So astronomers did what they always do when they hit the limits of direct observation. They started modeling. They built simulations of how galaxies form and evolve over cosmic time. They plugged in everything they knew about star formation, gas dynamics, dark matter halos, gravitational interactions, the whole machinery of galaxy assembly. Then they ran the simulations forward from the early universe to the present day and counted how many galaxies should exist at different masses and brightnesses. The models predicted that there should be a lot more small, faint galaxies than large, bright ones. That's consistent with what we see in the nearby universe. Dwarf galaxies outnumber giant galaxies by a huge margin. Our own Milky Way has dozens of small satellite galaxies orbiting it, and we keep finding more. But dwarf galaxies are hard to spot at large distances. They don't put out much light. If you're sitting billions of light years away, a dwarf galaxy is essentially invisible unless you stare at it for a very long time with a very sensitive instrument. The models suggested that the Hubble Deep Field was only scratching the surface. For every galaxy Hubble detected, there might be 10 or 20 or even 100 smaller, fainter galaxies lurking below the detection limit. If that were true, the total number of galaxies in the observable universe wasn't 70 billion. It was much, much higher. But how do you test that? How do you confirm the existence of galaxies you can't see? One way is to look at the cosmic background light. This is the diffuse glow of all the unresolved light in the universe. When you point a telescope at a patch of sky and measure the total brightness, even after subtracting out all the individual stars and galaxies you can identify, there's still a faint background glow left over. That glow has to be coming from something. And the most likely explanation is that it's coming from all the faint, distant, unresolved galaxies that are too dim to detect individually but collectively add up to a measurable signal. By carefully measuring the cosmic background light across different wavelengths and comparing it to the light coming from all the galaxies we can see, astronomers can estimate how much light is missing. How much of the total glow is coming from galaxies below the detection limit? The numbers from those measurements suggested that Hubble was missing a lot. Somewhere between half and two-thirds of all the light in the universe was coming from galaxies that weren't showing up in the deep field images. That implied a huge hidden population of faint galaxies. And if you extrapolate from that, accounting for all the small dim galaxies that Hubble couldn't detect, the total galaxy count shoots up, not to 100 billion, to several hundred billion, maybe more. Then in 2004, Hubble went deeper. The ultra-deep field pushed the exposure time to nearly 1 million seconds, spread over 4 months. It covered a slightly different patch of sky in the constellation Fornax, and it reached further back in time and detected fainter objects than the original deep field. The result was about 10,000 galaxies in a single image. 10,000. And again, that was just what Hubble could see. The models predicted that for every galaxy in the ultra-deep field, there were probably dozens more sitting below the brightness cutoff. The population of faint dwarf galaxies in the early universe was expected to be enormous. These weren't the massive, bright galaxies that dominated the nearby universe. These were the building blocks, small clumps of stars and gas that would eventually merge together over billions of years to form the larger galaxies we see today. Hierarchical assembly, that's the technical term. Galaxies grow by eating smaller galaxies. It's violent, it's messy, and it's been happening since the first stars lit up. By the mid-2000s, the consensus estimate for the total number of galaxies in the observable universe had climbed to around 100 to 200 billion. That number got repeated in textbooks, documentaries, press releases. It became the standard answer, and for a while it held. Then, in 2016, a team led by Christopher Consolis at the University of Nottingham published a paper that revised the number upward, dramatically upward. They combined data from Hubble's deep fields with new theoretical models that tried to account for the full population of galaxies across all masses and all epochs of cosmic history. They used a technique called number density evolution, which tracks how the density of galaxies changes over time as the universe expands and galaxies merge. Their conclusion was that the observable universe contains roughly 2 trillion galaxies, not 200 billion, 2 trillion. 10 times higher than the previous estimate. The reaction in the astronomy community was mixed. Some thought the new number was robust, that it finally accounted for all the faint galaxies that earlier estimates had missed. Others were more skeptical, pointing out that the uncertainties in the models were large and that the number could easily be off by a factor of 2 or 3 in either direction. But the 2 trillion figure stuck. It made headlines. It became the new standard answer, at least in popular science, and it underscored a basic truth about this kind of work. We are not counting galaxies the way you count apples in a basket. We are sampling a tiny fraction of the sky, building statistical models of what we think the rest of the sky looks like, and extrapolating from there. The error bars are huge, the assumptions are many, and the final number is only as good as the models we're using. Here's what makes this so tricky. The observable universe isn't everything. It's just the part of the universe we can see. Light from more distant regions hasn't had time to reach us yet, because the universe is only 13.8 billion years old, and light only travels so fast. There's a horizon, a boundary beyond which we can't see, not because there's nothing there, but because the light from those regions simply hasn't arrived yet. The size of the observable universe is determined by the speed of light and the age of the universe. Do the math, and you get a sphere roughly 93 billion light-years in diameter, centered on Earth. That's the volume we're talking about when we say 2 trillion galaxies. But the actual universe, the full cosmos, is almost certainly much larger than that, maybe infinitely larger. If that's true, then 2 trillion galaxies is just the galaxies in our little patch, a sample, not the full count. The total number of galaxies in the entire universe, not just the part we can see, could be orders of magnitude higher, or it could be infinite. We don't know. We can't know. The only number we can ever hope to estimate is the number within the observable horizon, and even that is hard. One of the big challenges is that galaxies aren't static, they're constantly changing. Stars are born, stars die, gas gets consumed, galaxies collide and merge. A galaxy that existed 10 billion years ago might not exist as an independent object today. It might have been swallowed by a larger neighbor. Or it might have merged with another galaxy to form something entirely new. When astronomers count galaxies in the Hubble Deep Field, they're not counting the same population at every distance. Nearby galaxies are being seen as they are now, or at least as they were a few million or a few 100 million years ago. Distant galaxies are being seen as they were billions of years ago, when the universe was younger and the galaxy population looked very different. So when you try to add up all the galaxies across all distances, you're not just counting objects in space, you're counting objects across time. Some of the galaxies you're counting in the distant universe have since merged and are now part of larger galaxies in the nearby universe. If you're not careful, you could end up double counting, or undercounting, or just getting confused. The models that Consolus's team used tried to account for this by tracking the merger history of galaxies over cosmic time. They estimated how many small galaxies in the early universe merged together to form the larger galaxies we see today. Then they added up the total number of distinct galaxies that have ever existed within the observable horizon, whether they still exist as independent objects or not. That's where the 2 trillion number comes from. It's not 2 trillion galaxies today. It's 2 trillion galaxy equivalents integrated over the full history of the observable universe. Some of those galaxies are still around. Many have merged. The distinction matters, but it also gets glossed over in a lot of popular accounts. When someone says there are 2 trillion galaxies, what they usually mean is that if you could freeze time at every point in cosmic history and count all the distinct galaxies that existed at each moment, then add them all up without double counting, you'd get something close to 2 trillion. It's a cumulative count, not a snapshot. And here's another wrinkle. The definition of what counts as a galaxy isn't as clear-cut as you might think. Is a small clump of a few million stars orbiting a larger galaxy its own galaxy, or just a satellite? At what point does a dense star cluster stop being a cluster and start being a dwarf galaxy? There's no sharp line. Astronomers have conventions, sure. They use criteria like total mass, size, whether the object is gravitationally bound, whether it has its own dark matter halo. But at the edges, the definitions get fuzzy. And when you're trying to count objects across the entire observable universe, including the faintest, dimmest, most marginal cases, those fuzzy edges add up to a lot of uncertainty. The Hubble Extreme Deep Field, released in 2012, tried to push even deeper. It combined over 2,000 individual exposures from Hubble, including data from the original Deep Field, the Ultra Deep Field, and several other surveys. The final image showed about 5,500 galaxies and reached back to within a few 100 million years of the Big Bang. Some of the galaxies in the XDF are so distant that their light has been traveling for over 13 billion years. We're seeing them as they were when the universe was less than 5% of its current age. At those distances, galaxies look primitive, small, irregular, often clumpy and asymmetric. These are the protogalaxies, the seeds that would eventually grow into the massive, well-ordered spirals and ellipticals we see nearby. And there are a lot of them. The XDF showed that the early universe was absolutely teeming with small star-forming galaxies, far more than anyone expected. That finding supported the idea that most of the galaxies in the universe are small and faint. The big bright galaxies get all the attention because they're easy to see, but numerically they're the minority. The universe is dominated by dwarfs. NASA's Hubble Legacy Field, published in 2019, went even further. It combined nearly 7,500 Hubble exposures taken over 16 years, stitching together data from multiple surveys into a single mosaic covering a slightly larger area than the previous deep fields. The legacy field contains about 265,000 galaxies spanning 13.3 billion years of cosmic history. 265,000 in one image. And that's still just a tiny sliver of the sky. The legacy field covers an area roughly the size of the full moon, which sounds big until you remember that the full sky contains about 41,000 square degrees, and the full moon only covers about half a degree. The legacy field is a fraction of a percent of the total sky, and even in that fraction, Hubble is still missing most of the faint galaxies. The 265,000 galaxies in the legacy field are just the ones bright enough to detect. The models predict that there are many times more galaxies in that same region sitting below Hubble's detection threshold. So how do astronomers estimate how many galaxies they're missing? One method is to take deep field data and bin the galaxies by brightness. Count how many galaxies fall into each brightness range. Then plot that distribution on a graph. What you typically see is that as you go to fainter brightnesses, the number of galaxies increases a lot. For every bright galaxy, there are 10 or 100 faint ones. The distribution follows a power law. And if you extrapolate that power law down to brightnesses below what your telescope can detect, you can estimate how many faint galaxies should be there even though you can't see them. The trick is knowing where to stop extrapolating. Does the power law keep going forever? Probably not. At some point, there has to be a lower limit. Galaxies below a certain mass just don't form efficiently. The gas is too hot, or radiation from nearby stars blows it away before it can collapse. Or dark matter halos below a certain size can't hold on to their gas long enough to make stars. So the faint end of the galaxy population doesn't keep rising forever. It flattens out. But where it flattens out and how steeply is still a matter of debate. Different models give different answers. And that uncertainty propagates directly into the total galaxy count. Another approach is to use what's called the galaxy luminosity function. This is a mathematical description of how many galaxies exist at each level of brightness. Measure the luminosity function in the nearby universe where you can see everything clearly. Then use models of galaxy evolution to predict how that function changes at earlier times when the universe was younger. Then integrate the luminosity function over all brightnesses and all redshifts, and you get a total galaxy count. The problem is that the models of galaxy evolution aren't perfect. They rely on assumptions about star formation rates, gas accretion, feedback from supernovae and black holes, the effects of dark matter, all of which are only partially understood. Change the assumptions and the predicted galaxy count changes, sometimes by a lot. The 2 trillion number from Consolis's team came from one particular set of assumptions. Other teams using different models have gotten different numbers, some higher, some lower. The uncertainty is real and it's large, probably a factor of 2 or 3 at least, maybe more. The James Webb Space Telescope is starting to chip away at that uncertainty. Webb's infrared sensitivity lets it see galaxies that were completely invisible to Hubble. Galaxies whose light has been redshifted so far into the infrared that Hubble's cameras just couldn't pick them up. In the first year of Webb operations, multiple teams reported finding large numbers of galaxies at redshifts above 10, 11, even as high as 14. These are galaxies forming in the first few 100 million years after the Big Bang. Hubble saw hints of a few candidates at those distances, but Webb is finding them by the dozens. That suggests the early universe had even more galaxies than the models predicted, which could push the total count higher. Or it could mean that the models were overestimating the number of faint galaxies at later times and underestimating them at early times. in which case the total might stay roughly the same, but the distribution changes. It's too early to say. Webb has only been operating for a couple of years. The data is still being analyzed. The full implications for galaxy counts won't be clear for another few years at least. One thing Webb has made clear is that the missing galaxies problem is real. Even in Webb's deepest images, you can see that the background between the resolved galaxies isn't perfectly dark. There's a faint diffuse glow, especially in the infrared. Some of that glow is instrumental noise, sure, but a lot of it is real light coming from galaxies that are too faint or too small to resolve individually. They're blending together into a kind of cosmic fog. That fog represents all the light from all the galaxies that no telescope has ever been able to separate out and count. And until we can either build telescopes sensitive enough to resolve those galaxies or develop better statistical methods to account for them, the total galaxy count will remain uncertain. Interestingly, the shift from 200 billion to 2 trillion galaxies didn't come from a sudden improvement in telescope technology. It came from better modeling. Hubble's data didn't change. What changed was our understanding of how much we were missing. The deep fields showed us a sample. The models told us how to scale that sample up to a full population, and the models said we were missing a lot more than we thought. That's how science works sometimes. You don't always need new data to get new answers. Sometimes you just need a better way of interpreting the data you already have. The 2 trillion number might be revised again in the future. It probably will be, but the trend is clear. Every time we look deeper, every time we push our telescopes to their limits, every time we refine our models and our statistical techniques, the number goes up, not down, up. The universe keeps revealing more galaxies, more structure, more complexity, and we're still only scratching the surface. There's something profoundly humbling about this. We've built telescopes that can see across 13 billion years of cosmic history. We've imaged individual galaxies forming in the infant universe. We've counted hundreds of thousands of galaxies in tiny patches of sky. And after all that, after all the deep fields and all the modeling and all the careful analysis, we still can't give you a precise number for how many galaxies there are. The best we can do is say it's somewhere in the trillions, maybe 2 trillion, maybe more, maybe less. The error bars are enormous, and that's okay, because the point isn't to get an exact count. The point is to understand the scale, to grasp, in some visceral way, just how absurdly large and populated the universe really is. 2 trillion galaxies, each one a separate world, each one containing billions or trillions of stars, each star potentially hosting planets, each planet potentially harboring life. The numbers stop meaning anything after a while. They're too big, too abstract, but the implication is clear. We are not alone in the universe. Not in the sense that there's definitely alien life out there, though the odds seem pretty good, but in the sense that we are not the only galaxy, not even close. We are one of trillions, a single note in a symphony so vast that we can't even hear most of it. And everything we've learned so far, every galaxy we've counted, every deep field we've taken, is just the opening movement. The rest of the universe is still out there, waiting to be explored. And here's the kicker. All of this, every galaxy we've talked about, every deep field image, every statistical model, every estimate of 2 trillion galaxies, all of it is just the visible matter, the stuff that emits light, the stuff we can see. There's something else out there, something that doesn't shine. Something that doesn't interact with light at all, but whose gravitational pull shapes every galaxy, every cluster, every structure we've ever observed. We call it dark matter, and it outnumbers the stuff we can see by a factor of 5 to 1. which means the universe we've been counting, the universe of galaxies and stars and gas, is just the tip of the iceberg. The rest is invisible, and it's bigger than everything else combined. All of this counting, all of these deep fields, all of these estimates of 2 trillion galaxies scattered across the observable universe, they all rest on one basic assumption, that the galaxies are real, that the light we see is coming from collections of stars held together by gravity, that the mass we infer from the brightness of those stars is actually there. For most of the 20th century, that assumption seemed safe. You could see the stars, you could measure their brightness, you could calculate how much mass they contained based on how much light they put out. The math worked, the galaxies stayed together, everything made sense. Until astronomers looked closer, and what they found was that the galaxies shouldn't be staying together at all. The stars were moving too fast, the mass wasn't where it was supposed to be, and the only way to make the numbers work was to admit that most of what holds a galaxy together is something we can't see, something that doesn't emit light, something that doesn't absorb light, something that doesn't interact with light at all. We call it dark matter, and it's not a footnote, it's not a minor correction to the models. It's most of the universe, about 5 times more massive than all the stars, gas, planets, and dust we've ever observed. Which means that everything we've been counting, every galaxy in every deep field, every estimate of how much ordinary matter exists in the cosmos, is just the visible tip of a much larger iceberg. The rest is invisible, and it's holding everything together. The story starts with a woman who spent decades staring at galaxies that weren't behaving. Vera Rubin was an astronomer at the Carnegie Institution in Washington, and in the 1970s she was doing something that sounds almost boring, measuring how fast stars orbit inside spiral galaxies. It's the kind of work that doesn't make headlines. You point a spectrograph at a galaxy, measure the Doppler shift of light coming from stars at different distances from the center, and calculate how fast those stars are moving. Then you plot the results on a graph, rotation speed versus distance. That's it. That's the job. And for most galaxies, the expectation was simple. Stars closer to the center should orbit faster. Stars farther out should orbit slower. Just like planets in our solar system, Mercury orbits the Sun much faster than Earth. Earth orbits faster than Jupiter. Jupiter orbits faster than Neptune. The farther you get from the Sun, the weaker the gravitational pull and the slower the orbital speed. That's basic Newtonian mechanics. Gravity weakens with distance. The same principle should apply to galaxies. Most of the mass in a spiral galaxy is concentrated in the bright central bulge, so stars near the center should feel a strong gravitational pull and orbit quickly. Stars out in the spiral arms, far from the center, should feel a weaker pull and orbit slowly. The rotation curve, the graph showing speed versus distance, should drop off as you move outward. That's what the equations predicted. That's what every model of galaxy dynamics said should happen. That's not what Rubin found. She looked at spiral galaxy after spiral galaxy, and the rotation curves were flat, not dropping, flat. Stars in the outer regions of these galaxies were moving just as fast as stars near the center. In some cases, they were moving even faster, and that made no sense. If you see something orbiting faster than it should, given the amount of mass you can account for, there are only 2 possibilities. Either the laws of gravity are wrong, or there's more mass than you're seeing. Rubin trusted gravity, so she started calculating how much unseen mass would be needed to explain the flat rotation curves. The answer was shocking. For the galaxies she studied, the amount of invisible mass required was enormous. 5 times the visible mass, 10 times in some cases. The stars you could see, the glowing gas clouds, the dust, all of that was just a small fraction of the total. Most of the galaxy's mass was something else. Something that didn't shine, something that exerted gravity but emitted no light, dark matter. Rubin wasn't the first person to suggest that invisible mass might be lurking in the universe. That idea went back to the 1930s. A Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a large group of galaxies bound together by gravity. He measured how fast the individual galaxies were moving within the cluster and used that to calculate the cluster's total mass. Then he added up the mass of all the visible galaxies and compared the two numbers. They didn't match, not even close. The galaxies were moving so fast that the cluster should have flown apart long ago unless there was far more mass holding it together than he could see. Zwicky called the missing mass dunkle materie, dark matter, but his idea didn't gain much traction. Zwicky had a reputation for being difficult, and his estimates were rough. The uncertainties were large enough that most astronomers dismissed the result as a measurement problem. Maybe the galaxies weren't moving as fast as he thought. Maybe the cluster was more massive than it appeared. Maybe he'd made a mistake somewhere in the math. The simplest explanation was that Zwicky was wrong, so the field moved on. For 40 years, the idea of dark matter sat on the shelf, mostly ignored. Rubin's work was different. She wasn't measuring a distant cluster with large uncertainties. She was measuring individual galaxies, close enough to resolve in detail. The rotation curves were clean, precise, repeatable. Other astronomers checked her work. They looked at other galaxies. They found the same thing, flat rotation curves. Everywhere. Galaxy after galaxy, the stars in the outer regions were moving too fast. The pattern was undeniable, and the only way to explain it was to accept that galaxies are surrounded by enormous halos of invisible mass, halos that extend far beyond the visible disk of stars. Halos that contain 5 to 10 times more mass than all the ordinary matter you can see. The visible galaxy, the part that shows up in photographs, is just the bright center of a much larger dark structure. Think of it like an iceberg. The part above water is the stars, the part below water is the dark matter, and the part below water is vastly larger. Rubin's discovery was initially hard to swallow. The idea that 90% of a galaxy's mass could be invisible felt almost ridiculous. How could something that massive remain completely undetected? But the data kept piling up. Other lines of evidence started pointing in the same direction. Galaxy clusters, for instance. Zwicky had been right all along. When astronomers measured the total mass of clusters using multiple methods, gravitational effects, X-ray emissions from hot gas, the motion of galaxies within the cluster, the numbers all agreed. Clusters contained far more mass than could be accounted for by visible matter. The missing mass was real, and it was everywhere. Then came gravitational lensing. Einstein's theory of general relativity predicts that massive objects bend space, and light traveling through that bent space follows a curved path. If a galaxy or a cluster of galaxies sits between us and a more distant object, the gravity of the foreground object acts like a lens, bending the light from the background object and distorting its appearance. Sometimes the distortion is subtle, a slight stretching or smearing. Other times it's dramatic, producing multiple images or giant arcs of light. By carefully measuring how much the light is bent, astronomers can calculate the total mass of the lensing object, not just the visible mass. The total mass, including everything that contributes to the gravitational field. When they did this for galaxy clusters, the results were unequivocal. The lensing mass was much larger than the visible mass, dark matter again, and the spatial distribution of the lensing mass didn't match the distribution of stars or gas. It was spread out in a diffuse halo, exactly as the rotation curve data suggested. One of the most famous examples is the Bullet cluster. It's actually two galaxy clusters that collided with each other a few 100 million years ago and are now passing through one another. When the clusters collided, the hot gas in each cluster, which is ordinary matter, interacted and slowed down. You can see that gas glowing in X-rays, sitting in the middle between the two clusters. But the galaxies themselves, which are mostly empty space, passed right through with almost no interaction. And when astronomers used gravitational lensing to map where most of the mass is, they found that the lensing signal wasn't centered on the hot gas, it was centered on the galaxies. That means most of the mass in the Bullet cluster isn't in the gas, it's in invisible halos surrounding the galaxies. Dark matter. The Bullet cluster is one of the cleanest pieces of evidence for dark matter because it separates the ordinary matter from the gravitational mass in a way that's hard to explain with any other theory. Then there's the cosmic microwave background, the faint afterglow of the Big Bang. The light that's been traveling through space for more than 13 billion years, carrying information about the state of the universe when it was only 380,000 years old. The temperature of that light isn't perfectly uniform. There are tiny fluctuations, hot spots and cold spots, that correspond to regions of slightly higher or lower density in the early universe. Those density fluctuations are the seeds that eventually grew into galaxies and clusters. Cosmologists can measure the pattern of those fluctuations with exquisite precision and use it to infer the total amount of matter in the universe, both ordinary and dark. The data from satellites like WMAP and Planck show that ordinary matter, the stuff made of protons, neutrons and electrons, makes up only about 5% of the total energy density of the universe. Dark matter makes up about 27%. The rest, about 68%, is something even stranger: dark energy. We'll get to that in a minute. But the point is that the cosmic microwave background gives us an independent measurement of how much dark matter exists, and it agrees with everything else. The rotation curves, the galaxy clusters, the gravitational lensing, all of it points to the same conclusion. The universe is dominated by invisible mass, so what is dark matter? That's the question that's been driving physicists crazy for decades. We know it's there. We know roughly how much of it there is. We know it doesn't emit, absorb, or reflect light. We know it interacts gravitationally with ordinary matter, but we don't know what it's made of. The leading hypothesis is that dark matter is composed of particles that don't interact with light or ordinary matter, except through gravity. These particles are often called WIMPs, weakly interacting massive particles. The idea is that the early universe produced a huge number of these particles during the Big Bang, and they've been floating around ever since, clumping together under gravity and forming the scaffolding on which galaxies and clusters are built. WIMPs would be invisible, but they'd have mass, so they'd exert gravitational pull. And because they don't interact with ordinary matter very much, they'd pass through walls, through planets, through you, without leaving a trace. Billions of dark matter particles could be streaming through your body right now, and you'd never notice. Physicists have built detectors deep underground, shielded from cosmic rays and other background radiation, hoping to catch a WIMP colliding with an atomic nucleus. So far, nothing. No confirmed detections. Decades of searching, and dark matter remains invisible in every sense of the word. There are other candidates: machos, massive compact halo objects. These would be chunks of ordinary matter that just don't shine. Things like brown dwarfs, black holes, or rogue planets floating in the halos of galaxies. Early surveys looked for machos by monitoring millions of stars and watching for gravitational lensing events caused by machos passing in front of them. They found a few events, but not nearly enough to account for all the dark matter. Machos can only explain a tiny fraction of the missing mass. Neutrinos were also considered for a while. These are subatomic particles that barely interact with anything and exist in enormous numbers throughout the universe. But neutrinos have very little mass, and they move too fast to clump together and form the kind of dense halos needed to explain galaxy rotation curves. The bulk of dark matter has to be something else, something cold, meaning it moves slowly, something that can clump. Something that's been stable for billions of years, and whatever it is, we haven't found it yet. The fact that we don't know what dark matter is should bother you. This isn't a minor gap in our knowledge. This is 95% of the universe. We've built a cosmological model that works extraordinarily well, that makes predictions we can test, that fits the data from dozens of independent observations. And at the heart of that model is a substance we can't see, can't touch, can't detect directly, and don't understand. We infer its existence entirely from its gravitational effects. It's like being a detective who solved a crime but never found the murder weapon. You know it was there. You know what it did. You just can't put your hands on it. And until we can, there's a piece of the story that's missing. If dark matter is the scaffolding that holds galaxies together, dark energy is the force tearing the universe apart. And it's even more mysterious. The story of dark energy begins in the late 1990s with a question that sounds simple but turned out to have a shocking answer. Is the expansion of the universe slowing down? Ever since Edwin Hubble discovered that galaxies are moving away from each other, cosmologists assumed that the expansion was gradually decelerating. Gravity, after all, is attractive. Every galaxy is pulling on every other galaxy. That pull should be slowing the expansion, maybe even reversing it eventually. The question was how much? Is the deceleration strong enough that the universe will eventually stop expanding and collapse back in on itself in a big crunch? Or is the expansion too fast for gravity to stop, meaning the universe will keep expanding forever, just more and more slowly over time? To answer that question, astronomers needed to measure the expansion rate at different points in cosmic history. They needed to look at distant objects whose light left them billions of years ago and compare the expansion rate back then to the expansion rate today. The tool they used was a specific type of supernova, type 1a. These are exploding stars that all blow up with roughly the same intrinsic brightness, making them excellent standard candles for measuring distances. If you know how bright a type 1a supernova truly is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. Combine that with the redshift, which tells you how fast the host galaxy is receding, and you get a direct measurement of the expansion rate at that distance. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, spent years finding and measuring distant Type 1a supernovae. They expected to find that the expansion was slowing down. That's what the models predicted. That's what everyone assumed. Instead, they found the opposite. The distant supernovae were fainter than they should have been, which meant they were farther away than expected, which meant the expansion of the universe had been slower in the past and had sped up over time. The universe wasn't decelerating, it was accelerating. Galaxies weren't just moving away from each other, they were moving away faster and faster. Something was pushing them apart. Something with enough oomph to overcome the attractive pull of all the matter, dark and ordinary, in the universe. The discovery won the Nobel Prize in Physics in 2011. It also shattered cosmology, because there was no obvious explanation for what could be causing the acceleration. The term for whatever is driving the acceleration is dark energy. It's called dark because we can't see it, and it's called energy because, well, we don't have a better name. Unlike dark matter, which clumps and pulls things together gravitationally, dark energy appears to be smoothly distributed throughout space and acts as a kind of anti-gravity. It doesn't pull, it pushes, and the more space there is, the stronger the push becomes. As the universe expands, the density of matter and dark matter decreases. You're spreading the same amount of stuff over a larger volume. But dark energy doesn't dilute. Its density stays constant, or at least very close to constant, as space expands. So over time, dark energy becomes more and more dominant. In the early universe, when everything was packed close together, matter and dark matter dominated. Gravity was winning. The expansion was slowing down. But as the universe expanded and matter spread out, dark energy started to take over. About 5 or 6 billion years ago, dark energy became the dominant force, and the expansion began to accelerate. That acceleration is still going on, and based on current observations, it's going to keep going on forever. The simplest explanation for dark energy is something Einstein introduced a century ago and later called his biggest blunder: the cosmological constant. Einstein added a term to his equations of general relativity that represented a kind of inherent energy density in empty space, a constant outward pressure that would counteract gravity and keep the universe static, which is what everyone thought the universe was at the time. When Hubble discovered the expansion, Einstein dropped the cosmological constant and supposedly said introducing it was his greatest mistake. Turns out he might have been right the first time. If space has a baseline energy density that doesn't change as the universe expands, then that energy would produce exactly the kind of accelerating expansion we observe. The cosmological constant is often associated with the idea of vacuum energy. Quantum field theory predicts that empty space isn't really empty. It's filled with virtual particles constantly popping in and out of existence. Those fluctuations should contribute to the energy density of space. The problem is that when you calculate how much vacuum energy quantum field theory predicts, the number is absurdly large, about 10 to the power of 120 times larger than the observed dark energy density. That's not a rounding error. That's a catastrophic failure of the theory. Why the vacuum energy is so much smaller than it should be is one of the biggest unsolved problems in physics. Some cosmologists think the cosmological constant is the right answer, and we just don't understand how to calculate it correctly. Others think dark energy is something more exotic. The other main candidate is called quintessence. Unlike the cosmological constant, which is truly constant, quintessence is a dynamic field that can change over time. Its energy density would vary as the universe evolves. Quintessence models are more flexible than the cosmological constant, and they can potentially explain why dark energy became important when it did, rather than dominating the universe from the beginning. But there's no direct evidence for quintessence, and it introduces a whole new field that we know nothing about. It's speculative, and in science, the simplest explanation that fits the data is usually preferred. For now, the cosmological constant is the leading candidate, even though we don't understand why its value is what it is. The combined picture is this. The universe is made of 3 main components. Ordinary matter, the stuff we can see and touch, makes up about 5% of the total energy density. Dark matter, invisible but gravitationally interacting, makes up about 27%. Dark energy, the mysterious force driving the accelerating expansion, makes up about 68%. Add it up, and you get a universe where 95% of reality is something we've never directly observed. We infer dark matter from rotation curves, gravitational lensing, and the cosmic microwave background. We infer dark energy from the dimming of distant supernovae and the changing expansion rate, but we can't see either one. We can't put them in a lab and study them. We only know they exist because of their effects. If you want to feel cosmically insignificant, this is a good place to start. Not only are we sitting on one planet orbiting one star in one galaxy among 2 trillion galaxies, but the galaxy itself is mostly made of something we can't see, and the space between galaxies is filled with an energy field we don't understand that's pushing everything apart. We're the 5%, the visible minority, the footnote. And everything we've learned about the universe, every deep field, every galaxy count, every measurement of distances and expansion rates, all of it depends on understanding the 95% we can't see. Dark matter and dark energy don't just exist as abstract concepts. They shape the universe. Dark matter is the reason galaxies formed at all. In the early universe, after the Big Bang, matter was spread almost uniformly through space. Almost. There were tiny density fluctuations, regions where matter was slightly more concentrated. Those fluctuations are visible today in the cosmic microwave background. But ordinary matter alone couldn't have collapsed into galaxies fast enough. Radiation pressure from the hot early universe would have blown it apart before gravity could pull it together. Dark matter changed that. Because dark matter doesn't interact with light or radiation, it could start clumping together immediately, unimpeded. The dark matter collapsed first, forming gravitational wells. Then ordinary matter fell into those wells, pulled in by the gravity of the dark matter halos. Stars formed, galaxies assembled, all because dark matter built the framework first. Without dark matter, the universe would look completely different. Maybe no galaxies at all. Maybe just a thin, diffuse fog of hydrogen and helium expanding forever with no structure, no stars, no planets, no us. Dark energy determines the ultimate fate of the universe. If dark energy stays constant, as the cosmological constant predicts, the universe will keep accelerating forever. Galaxies will continue to move apart. Eventually, billions of years from now, galaxies outside our local group will recede so fast that their light will no longer be able to reach us. The observable universe will shrink, the sky will go dark, stars will burn out. New stars will stop forming as galaxies run out of gas. The universe will grow cold, empty, and dark. That's called the Big Freeze, or heat death. Not a pleasant ending, but a long, slow one. If dark energy is something more dynamic, if it can change over time, other possibilities open up. Maybe dark energy will weaken, and the universe will stop accelerating. Maybe it will strengthen, and the acceleration will become so extreme that it tears galaxies, stars, planets, even atoms apart in a big rip. We don't know. The only way to find out is to keep measuring the expansion rate and watching how dark energy behaves over time. For now, the universe is expanding, accelerating, and filled with invisible mass and invisible energy. Dark matter holds galaxies together. Dark energy pushes them apart, and somewhere in the balance between those two forces, structures form. Galaxies cluster together into groups. Groups cluster into larger structures. Those larger structures form filaments and sheets and voids, a cosmic web of matter threading through the universe on the largest scales imaginable. That web is the next part of the story. And the only reason it exists, the only reason the universe has any large-scale structure at all, is because of the invisible architects, the dark matter pulling matter together, and the dark energy keeping space expanding. 95% of reality, shaping everything we see, and we can't touch any of it. That's the universe we live in, and it's just starting to get strange. 95% of reality is invisible. Dark matter holds galaxies together. Dark energy tears the universe apart. Those two forces, pushing and pulling, shaping and accelerating, sound like they should be fighting each other to a standstill. They're not. They're collaborating, building something so large that the word structure barely does it justice. Something that stretches across hundreds of millions of light years and connects every galaxy cluster in the observable universe into a single coherent pattern. We call it the cosmic web, and it is, without exaggeration, the largest known structure in existence. When you look at galaxies through a telescope, they don't appear to be arranged randomly. That much has been clear since the 1920s, when Edwin Hubble and others started cataloging their positions on the sky. Galaxies cluster. They group together, not in neat rows or grids, but in clumps. Some regions of space are packed with galaxies, others are nearly empty. For a long time, astronomers assumed this clustering was local. A few galaxies here, a few there, bound together by their mutual gravity, but no grand organizing principle beyond that. Then they started counting galaxies over larger and larger regions, and the pattern became undeniable. The clusters weren't isolated, they were connected, threaded together by fainter chains of galaxies that stretched between the bright nodes. And between those chains, vast empty regions where almost nothing existed, not just sparse, empty. Voids so large that light takes hundreds of millions of years to cross them. The galaxies weren't scattered at random. They were woven into a network, a web. The term cosmic web is recent, coined sometime in the 1990s, but the observations that led to it go back much further. In the 1950s and 60s, astronomers began the painstaking work of mapping galaxy positions in 3 dimensions. Not just their locations on the sky, which gives you 2 dimensions, but their distances as well. That required measuring redshifts for thousands of galaxies, one at a time, using spectrographs that could only observe a single object per night. It was slow work, tedious work, the kind of project that takes decades. But by the 1970s, enough data had accumulated to reveal something strange. Galaxies were arranged in sheets and filaments, long thread-like structures stretching across tens of millions of light years. And where those filaments intersected, you'd find clusters, dense concentrations of hundreds or thousands of galaxies bound together by gravity. The Coma cluster, the one Fritz Zwicky studied in the 1930s and found to be full of dark matter, sits at one of these intersections, a node in the web. One of the first major surveys to map this structure in detail was the CFA Redshift Survey, conducted by astronomers at the Harvard-Smithsonian Center for Astrophysics in the late 1970s and early 1980s. They measured the redshifts of more than 2,000 galaxies within a wedge-shaped slice of the sky. When they plotted the results, the pattern was startling. The galaxies weren't distributed smoothly. They formed distinct structures, walls, sheets, filaments, and between them, enormous voids. One of the largest voids they found, later named the Boots Void, spans roughly 330 million light-years. Inside that void, there are almost no galaxies, just empty space. The discovery made headlines. Astronomers called it the Great Wall, though technically the wall was the sheet of galaxies surrounding the void, not the void itself. Either way, the implication was clear. The universe had structure on scales far larger than anyone had anticipated. Galaxies weren't just clustered into groups. They were organized into a vast, interconnected network. Why? Why would galaxies arrange themselves like this? The answer, predictably, comes back to dark matter. In the early universe, just after the Big Bang, matter was spread almost uniformly through space. Almost. There were tiny fluctuations in density, regions where matter was packed slightly more tightly than average. Those fluctuations are visible today in the cosmic microwave background, the faint glow of radiation left over from when the universe was only 380,000 years old. The temperature variations in that glow are minuscule, less than 1 part in 100,000, but they're real. And they're the seeds, the starting point for everything that came after, because gravity amplifies tiny differences. A region that's slightly denser than average pulls in more matter from its surroundings. As it pulls in more matter, it becomes even denser, which makes its gravitational pull even stronger. The process feeds on itself. Dense regions get denser, sparse regions get sparser. Over billions of years, the tiny ripples in density grew into the massive structures we see today. But there's a problem. Ordinary matter alone couldn't have done this. Not fast enough. In the early universe, ordinary matter was hot. It was interacting with radiation, being pushed around by photons. That radiation pressure resisted gravity, tried to smooth things out. If all you had was ordinary matter, the density fluctuations would have been washed out before they had a chance to grow. But dark matter doesn't interact with radiation. It doesn't feel radiation pressure. It can clump together freely, unimpeded by the light and heat that were slowing down ordinary matter. So dark matter collapsed first. It formed the scaffolding. Dense clumps of dark matter grew into massive halos, and those halos pulled ordinary matter in after them. Gas fell into the dark matter wells, compressed, heated, and eventually ignited into stars. Galaxies formed inside the dark matter halos, but the halos themselves weren't isolated. They were part of a larger network, a web of dark matter filaments stretching across the universe. The visible cosmic web, the one we see when we map galaxy positions, is just the luminous trace of that deeper, invisible structure. The dark matter web came first, the galaxies followed. Simulations make this clear. Starting in the 1980s, cosmologists began using computers to model how structure forms in the universe. These are called N-body simulations. N stands for the number of particles in the simulation, sometimes a few million, sometimes billions. Each particle represents a clump of dark matter. You start the simulation shortly after the Big Bang. Set the initial conditions based on the density fluctuations measured in the cosmic microwave background, then let the simulation run forward in time. Gravity does the rest. The particles attract each other, they clump together. Small clumps merge into larger clumps. Over billions of simulated years, the distribution of dark matter evolves from a nearly uniform fog into a complex network of filaments and nodes. And when you plot the final result, it looks exactly like the cosmic web we observe. Long thread-like filaments connecting dense clusters at the intersections, vast voids in between. The match between the simulations and the real universe is one of the most impressive confirmations of the standard cosmological model. We can't see the dark matter directly, but we can simulate how it should behave, and the simulation produces a structure that matches the distribution of galaxies we observe. That's not a coincidence. It's evidence that we're on the right track. The cosmic web has components, specific features that show up in every large-scale map. The first are filaments. These are the threads of the web, long, thin structures, typically a few million light-years wide and stretching for hundreds of millions of light-years. Filaments contain galaxies, but they're not packed densely. The galaxies are strung out like beads on a string. separated by millions of light-years of mostly empty space. But the filaments themselves are not empty. They contain gas, tenuous, diffuse, hard to detect, but it's there. Astronomers have been able to observe this gas indirectly by looking at how it absorbs light from distant quasars. When light from a quasar passes through a filament on its way to Earth, the hydrogen gas in the filament absorbs specific wavelengths, leaving dark lines in the quasar's spectrum. This is called the Lyman alpha forest, and it's one of the main tools for mapping the intergalactic medium, the gas that fills the space between galaxies. More recently, in 2019 and again in 2021, astronomers detected diffuse Lyman alpha emission directly from filaments, not absorption, emission. The gas itself was glowing, lit up by the ultraviolet radiation from nearby galaxies. These detections are rare and difficult because the signal is so faint, but they confirm that filaments are real physical structures, not just statistical artifacts of how galaxies are distributed. The second component of the cosmic web is nodes. These are the intersections where multiple filaments meet, and at those intersections you find galaxy clusters. Dense concentrations of hundreds or thousands of galaxies bound together by gravity. Clusters are the most massive gravitationally bound structures in the universe. The largest ones weigh more than a quadrillion suns, 1,000 trillion solar masses. Most of that mass is dark matter, of course. The galaxies themselves account for only a few percent. Another 10 to 15% is hot gas trapped in the cluster's gravitational well, glowing in X-rays at temperatures of tens of millions of degrees. The rest is dark matter. And the dark matter halo of a large cluster extends far beyond the visible galaxies, stretching out along the filaments that feed into the node. Material flows along the filaments toward the clusters, pulled in by gravity. Clusters are the endpoints, the places where matter accumulates, where galaxies collide and merge, where the cosmic web becomes dense and bright. The third component is voids, and voids are the strangest part of the web because they're defined by what isn't there. Voids are enormous regions of space where galaxies are rare or absent. They're not perfectly empty. A few galaxies exist inside voids, typically small, dim, isolated objects. But the average density of matter in a void is far below the cosmic average. Voids occupy most of the volume of the universe. If you drew a map of the cosmic web and colored in the filaments and clusters, you'd realize that the colored regions only take up maybe 10 to 20% of the total space. The rest, 80 to 90%, is voids. The universe is mostly emptiness, threaded by thin filaments of light. That's the structure. That's what emerged from the Big Bang after 13.8 billion years of gravitational collapse. A foam, a sponge, a web, take your pick of metaphors. They all capture something true about the shape of the universe. Mapping the cosmic web requires surveying huge numbers of galaxies across large volumes of space. One of the landmark projects that did this is the Sloan Digital Sky Survey, or SDSS, which began observations in 2000. The survey used a dedicated telescope in New Mexico to systematically photograph the sky in multiple wavelengths and measure the spectra of millions of galaxies. The goal was to create a three-dimensional map of the universe, tracing the positions and distances of galaxies out to billions of light-years. Over the course of more than 2 decades, SDSS has mapped more than 3 million galaxies, hundreds of thousands of quasars, and countless other objects. The resulting maps are stunning. When you plot galaxy positions in 3 dimensions, the cosmic web jumps out at you. Sheets and filaments and voids, all woven together in a structure so large it takes your breath away. The data from SDSS and similar surveys have been used to test cosmological models, measure the expansion rate of the universe, study dark energy, and probe the distribution of dark matter. It's one of the most productive astronomical projects ever conducted, and it showed, beyond any reasonable doubt, that the cosmic web is real. But galaxies only trace the visible matter. If you want to map the dark matter, you need a different technique. That's where gravitational lensing comes in. When light from a distant galaxy passes near a massive foreground object, a cluster, or a large concentration of dark matter, the gravity of the foreground object bends the light. This bending distorts the appearance of the background galaxy, sometimes subtly stretching it into an arc, sometimes dramatically splitting it into multiple images. By carefully measuring how much the light is distorted, astronomers can calculate the total mass of the foreground object. Not just the visible mass, the total mass. And by doing this for many background galaxies spread across the sky, they can build a map of the dark matter distribution in 3 dimensions. This technique is called weak gravitational lensing, and it's become one of the most powerful tools in cosmology. It lets you see the invisible. It turns dark matter into something you can map, measure, and study. One of the most impressive uses of gravitational lensing came from the Hubble Space Telescope. A team of about 70 astronomers from around the world used Hubble to observe a single region of sky for more than 1,000 hours, collecting 575 overlapping images. The observations reached back to roughly halfway to the beginning of the universe, capturing light from galaxies and clusters at multiple distances. By analyzing the distortions in the shapes of distant galaxies, the team reconstructed a 3-dimensional map of the dark matter in that region. It was the first direct 3-dimensional look at how dark matter is distributed on large scales. And the map showed exactly what the simulations predicted: a web, filaments connecting clusters, voids in between. The dark matter and the visible galaxies traced the same structure because the visible galaxies formed inside the dark matter scaffolding. The lensing map was proof, visual, measurable proof, that the cosmic web isn't just a pattern in galaxy positions, it's a pattern in the distribution of mass itself. Dark matter and all. Hubble also made the first detailed map of a single filament. The target was a massive galaxy cluster called MAX J0717, one of the largest clusters known. The cluster sits at the intersection of multiple filaments, and Hubble's observations traced one of those filaments stretching out from the cluster core. The map showed that the filament contains galaxies, hot gas, and a huge amount of dark matter. The filament is acting like a pipeline, funneling matter into the cluster, feeding it. Over billions of years, the cluster has grown by consuming material flowing in along the filaments. This is how structure grows in the universe, not all at once, gradually, piece by piece. Material flows along the web, accumulating at the nodes, building clusters and superclusters over cosmic time. The James Webb Space Telescope is now pushing these observations further. One of Webb's largest surveys, called Webb, is mapping the cosmic web at unprecedented depth, tracing galaxies back to when the universe was about 1 billion years old. That's early. The cosmic web at that epoch was still forming. The filaments were thinner, the clusters were smaller. Galaxies were just starting to fall into the dark matter halos. By comparing the structure of the web at different times, astronomers can watch the web grow. They can see how the universe evolved from a relatively smooth distribution of matter into the complex, structured cosmos we see today. And they can test whether the growth matches the predictions of the Standard Model. So far it does. The cosmic web at high redshift looks like a younger, less evolved version of the web nearby. The pattern is the same, just less pronounced. Which is exactly what you'd expect if gravity has been building structure over time, pulling matter into denser and denser concentrations as the universe expands. The scale of the cosmic web is difficult to grasp. The largest known structures in the web are superclusters. These are clusters of clusters, vast complexes containing dozens or hundreds of galaxy clusters, all connected by filaments. The Laniakea supercluster, which includes our own Milky Way, spans about 520 million light-years. That's the distance light travels in 520 million years. And Laniakea is just one supercluster among many. There are others just as large scattered across the observable universe, and they're all part of the same web, all connected, all influenced by the same gravitational forces that have been shaping structure since the first stars lit up. The cosmic web is the universe's largest known structure in standard cosmology. There's nothing bigger, nothing more organized, nothing that stretches across more space, and it's all held together by gravity. The gravity of dark matter, mostly. The invisible scaffolding that makes up most of the mass in the universe and determines where galaxies form, how they move, and where they're going. The cosmic web matters for galaxy evolution. Galaxies don't evolve in isolation, they're constantly interacting with their environment. Gas flows in along filaments, feeding star formation. Galaxies collide and merge when they meet in clusters. The hot gas in clusters strips gas out of galaxies, quenching star formation and turning bright blue spiral galaxies into dim red ellipticals. The web controls where these interactions happen and how often. Galaxies in dense clusters evolve differently from galaxies in filaments or voids. The environment shapes the galaxy, and the environment is determined by the cosmic web. If you want to understand why galaxies look the way they do, why some are still forming stars and others are dead, you have to understand their place in the web, where they sit, what kind of neighborhood they're in, how much material is flowing past them. The web is the context, the stage on which the drama of galaxy evolution plays out. The cosmic web also affects the future of the universe, because the web is a product of gravity, and gravity is fighting against the expansion of space. In dense regions, where matter has collapsed into clusters and filaments, gravity is strong enough to hold things together. Clusters will stay bound, they won't be torn apart by the expansion. But the voids are a different story. Voids are expanding. As dark energy drives the overall expansion of the universe, the voids grow larger, the filaments stretch, the distance between clusters increases. Eventually, billions of years from now, the voids will become so large that the filaments will thin out and break. Clusters will lose contact with each other. The cosmic web will dissolve. Each cluster will become an isolated island, surrounded by empty space that's expanding faster than light can cross it. Galaxies outside our local cluster will recede beyond the horizon. The observable universe will shrink. The web we see today is temporary, a snapshot of a universe in transition. Billions of years ago, the web was just starting to form. Billions of years from now, it will be gone. We happen to be living at a time when the web is fully formed and visible. That's not a privilege we should take for granted. There's something almost poetic about the cosmic web. Galaxies, those enormous collections of hundreds of billions of stars, are not the fundamental units of structure. They're just the bright spots, the nodes where light accumulates. The real structure is the web itself, the dark matter filaments, the invisible threads that connect everything. And we can only see the web because galaxies light it up. Without the stars, without the gas, the web would still be there. It would still exist. It would still determine how matter moves and where it accumulates. But it would be completely invisible. We would have no idea it was there. The fact that we can map it, that we can trace its structure across billions of light years, is only possible because gravity pulled gas into the filaments and lit it up. The universe made itself visible. It built a structure, then filled that structure with light so we could see it. That seems almost intentional. It's not, of course. It's just physics. But the result is striking. The largest structure in the universe, the cosmic web, is a collaboration between the visible and the invisible, between the 5% of ordinary matter that shines and the 95% of dark matter and dark energy that shapes everything else. Standing at the edge of that web, metaphorically speaking, you'd see filaments stretching in every direction, chains of galaxies threading through the void, some bright, some faint, some nearby, some so distant their light has been traveling for billions of years. And if you could zoom out, pull back far enough to see the entire observable universe at once, you'd see the web in its full glory. A vast network of light and matter stretching from one horizon to the other, clusters at the nodes, filaments connecting them, voids in between. And underneath it all, invisible but undeniable, the dark matter scaffolding that holds the whole thing together. That's the cosmic web, the universe's skeleton, its backbone, its largest structure. And every galaxy in every deep field, every object in every survey, every cluster, every filament, every void, all of it is part of that web, including us, including the Milky Way. We're sitting in a filament right now. Part of the Laniakea supercluster, one thread in a tapestry so large it takes light 500 million years to cross it. That's where we are. That's our address in the universe. Not just a planet, not just a star, not just a galaxy, a thread in the cosmic web. One tiny glowing strand in a network that spans the observable cosmos. And now that we've zoomed out far enough to see the web, far enough to understand how galaxies are organized across the universe, it's time to zoom back in. Because while the web tells us where galaxies are and how they're connected, it doesn't tell us what's happening inside them. What makes galaxies shine? What turns cold gas into stars? What keeps some galaxies blazing with new light while others fade into silence? To answer those questions, we need to step inside, to look past the outer structure and peer into the heart of a galaxy where the real action is, where stars are born. We've spent most of this video zooming out, from 1 galaxy to 2 trillion, from Edwin Hubble discovering Andromeda to the James Webb Space Telescope finding galaxies at the edge of the observable universe. From the Hubble Deep Field showing thousands of galaxies in a patch of sky no bigger than a grain of sand, to the cosmic web stretching across 500 million light years, threading the entire universe together with filaments of dark matter. The scale has been relentless. Every step outward has made us smaller, but now it's time to stop, to zoom back in. Because knowing that 2 trillion galaxies exist doesn't tell you what a galaxy actually is, what it's made of, what happens inside it, what keeps it shining. And if you're going to understand the universe, if you're going to grasp what those trillions of galaxies really mean, you need to understand the machinery, the processes happening inside every one of them, the birth of stars, the death of stars, the black holes hiding at the center, the gas and dust cycling through generations of creation and destruction. Galaxies aren't static objects. They're not museums. They're factories, engines of transformation that have been running for billions of years, turning raw hydrogen into everything else, into carbon and oxygen and iron, into planets and atmospheres and, if we're lucky, into life. This is the story of what happens inside a galaxy, the cradle of stars, the heart of everything. Let's start with the basics. What does a galaxy actually look like up close? Not as a distant blob of light in a deep field image, but as a real physical structure you could, hypothetically, fly through. The answer depends on what kind of galaxy you're looking at, because galaxies come in types, and those types matter. The most familiar kind, the kind that dominates the popular imagination, is the spiral galaxy. NASA describes them as giant rotating pinwheels, a pancake-like disk of stars and gas, flat and wide, spinning around a central bulge. The disk is where most of the action happens. It's where the spiral arms are, those bright sweeping curves that wrap around the galaxy's center like the arms of a hurricane. The spiral arms aren't solid structures. They're not fixed in place. They're density waves, regions where stars and gas are temporarily compressed as they move through their orbits. Think of it like a traffic jam on a highway. The cars aren't stuck, they're moving. But there's a bottleneck, a region where the density of cars is higher. The jam itself moves slower than the cars. The same thing happens in a spiral galaxy. Stars orbit the center at their own speeds, but as they pass through the spiral arms, they slow down slightly, bunch up, and then move on. The arms persist because new stars keep entering them. And while the stars are bunched up in the arms, the gas gets compressed. Compressed gas collapses, and when it collapses, it forms stars. This is why spiral arms are so bright. They're not brighter because they contain more stars overall. They're brighter because they contain more young stars. And young stars, especially the massive ones, burn hot and blue and put out enormous amounts of light. The biggest, brightest stars in a spiral galaxy live in the arms because that's where they were born. And because massive stars don't live long, only a few million years before they explode as supernovae, they never have time to drift far from their birthplace. By the time a massive blue star leaves the spiral arm, it's already dying. The arms are star nurseries. The disk as a whole contains stars of all ages, but the arms are where the youngest, brightest, most energetic stars are concentrated. That's what makes the arms visible. That's what gives a spiral galaxy its shape. At the center of the disk sits the bulge, a dense, roughly spherical collection of older stars packed tightly together. The bulge doesn't have much gas or dust. Most of the star formation happened there billions of years ago, early in the galaxy's history. Now the bulge is mostly quiet. The stars are older, cooler, redder. They're not putting out as much light per star, but there are so many of them crammed into such a small volume that the bulge still shines brightly. Surrounding the entire galaxy, extending far beyond the visible disk, is the halo. A vast, diffuse region containing old stars, globular clusters, and, most importantly, dark matter. Lots of dark matter. The halo is where most of a galaxy's mass actually resides, even though you can't see it. The visible part of a spiral galaxy, the part that shows up in photographs, is just the glowing core of a much larger dark matter structure. The disk is the centerpiece, sure, but it's sitting inside a halo that extends 10 times farther in every direction. The Milky Way, our own galaxy, is a spiral, a large one, about 100,000 light-years across in its visible disk. It contains somewhere between 200 billion and 400 billion stars, depending on whose estimate you trust, and it's rotating. The Sun orbits the galactic center at about 220 kilometers per second. At that speed, it takes roughly 230 million years to complete one full orbit. The last time the Sun was in this part of the galaxy, dinosaurs were just starting to evolve. The next time it comes back around, if the Sun is still shining and the Earth is still habitable, which is a big if, whatever lives here won't recognize the night sky. the stars will have moved. The constellations will be gone. The galaxy keeps turning, and everything in it goes along for the ride. Elliptical galaxies are different, completely different. They don't have disks, they don't have spiral arms. They're round, or oval, or somewhere in between. They look like fuzzy balls of light, smoothly glowing with no obvious structure, no lanes of dust, no bright blue star-forming regions. Just a smooth distribution of old red and yellow stars. Ellipticals range in size from dwarfs, which contain only a few million stars, to giants, which can contain more than 1 trillion. The giant ellipticals are the largest galaxies in the universe. They sit at the centers of galaxy clusters, fat and red and ancient, surrounded by smaller galaxies that they've been slowly cannibalizing over billions of years. Ellipticals form differently than spirals. Most of them are thought to be the result of galaxy mergers. When two spiral galaxies collide, their disks get shredded. The stars don't actually hit each other because galaxies are mostly empty space, but the gravitational interactions are violent. Stars get flung into chaotic orbits. The gas clouds collide and compress, triggering a burst of star formation so intense it's called a starburst. All the gas gets used up in a few 100 million years, and when it's over, you're left with a big, round, gas-poor elliptical galaxy, full of stars but with nothing left to make new ones. Ellipticals are the fossils of galactic violence. They're what you get when spirals collide and destroy each other's structure. And because they have so little gas and dust, they don't form new stars, not in significant numbers. They're aging gracefully, slowly dimming as their stars burn out one by one, with no replacements. Every elliptical galaxy that's been studied in detail contains a supermassive black hole at its center, every single one. The black holes in ellipticals tend to be bigger than the ones in spirals, which makes sense because ellipticals formed from mergers, and when galaxies merge, their central black holes merge too. The combined black hole ends up with the mass of both parents. Do that enough times over billions of years, and you end up with a monster. A black hole weighing billions of times the mass of the Sun, sitting at the heart of a dead galaxy, slowly accreting whatever stray gas drifts too close. There are other types, of course. Lenticular galaxies, which look like a cross between spirals and ellipticals. They have disks and bulges but no spiral arms and very little gas. They're transition objects, spirals that ran out of fuel, irregular galaxies which don't fit any neat category. They're lumpy, chaotic, often the result of gravitational interactions with nearby galaxies. Some irregulars are forming stars at prodigious rates, others are just small and messy. The Magellanic Clouds, two small galaxies orbiting the Milky Way, are irregulars. They're close enough that you can see them with the naked eye from the southern hemisphere, and they've been distorted by the Milky Way's gravity into their current odd shapes. Galaxies aren't static, they evolve. They change shape, they collide, they merge, they steal gas from each other. The type of galaxy you see today is just a snapshot, a moment in a history that spans billions of years, and that history is written in the stars. Stars are the reason galaxies shine. Without stars, a galaxy would just be a cloud of invisible gas and dark matter. Useful for holding things together gravitationally, but not much to look at. Stars turn mass into light. They do this through nuclear fusion, the process that powers every star in every galaxy. Hydrogen atoms smash together under enormous pressure and temperature in a star's core, fusing into helium and releasing energy. That energy works its way out through the star's layers and escapes as light. The process is astonishingly efficient. A single kilogram of hydrogen fused into helium releases more energy than burning 10 million kilograms of coal. and stars have a lot of hydrogen. The Sun, an average star by most standards, has been fusing hydrogen for about 4.5 billion years. It's about halfway through its fuel supply. It'll keep shining for another 5 billion years before it runs out. But stars don't all live the same lifespan. Massive stars, the ones that are 10 or 20 or 50 times heavier than the Sun, burn through their fuel in just a few million years. They're profligate, wasteful. They fuse hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Each fusion stage releases less energy and lasts less time. By the time a massive star starts fusing silicon into iron in its core, it has less than a day left. Iron doesn't fuse. Fusing iron requires energy instead of releasing it. So the moment a massive star builds up an iron core, the core collapses. In less than a second, the core goes from the size of the Earth to the size of a city. The outer layers of the star, no longer supported, fall inward and then rebound off the collapsing core. The star explodes, a supernova. For a few weeks, that single exploding star can shine as brightly as an entire galaxy. And in the process, it creates and scatters all the heavy elements beyond iron. Gold, silver, uranium, everything that doesn't get made in the steady fusion reactions inside stars gets made in the chaos of a supernova. Every atom of gold in every piece of jewelry ever worn was forged in a supernova explosion billions of years ago. The star died, the elements scattered into space, and eventually some of that enriched gas collapsed to form new stars and planets and us. Supernovae don't just enrich the interstellar medium with heavy elements, they also blast huge amounts of energy into the surrounding gas. That energy heats the gas, ionizes it, drives it outward in expanding bubbles called supernova remnants. For tens of thousands of years, a supernova remnant can glow in X-rays as the hot gas cools and mixes with the surrounding medium. The energy from supernovae, combined with the intense radiation from massive young stars, can blow gas out of a galaxy entirely. This is called galactic winds, and it's one of the main ways galaxies regulate their own star formation. If too many massive stars form at once, their combined energy output can heat the gas so much that it can't collapse to form new stars. Star formation shuts down. The galaxy goes quiet for a while until the gas cools and falls back in. Then the cycle starts again. Galaxies breathe. They inhale gas from their surroundings, form stars, exhale the gas in winds and supernovae, then inhale again. The cycle has been running for billions of years, and it's why galaxies still have gas left to form stars today. If all the gas had been turned into stars in the first billion years, galaxies would have gone dark long ago. Instead, they pace themselves, regulated by feedback from the very stars they create. At the center of almost every massive galaxy sits a supermassive black hole. Not a stellar mass black hole, the kind that forms when a massive star collapses. A supermassive black hole. Millions or billions of times the mass of the Sun. The Milky Way's central black hole is called Sagittarius A star. It weighs about 4 million solar masses and sits roughly 26,000 light-years from Earth. We can't see the black hole itself, obviously. Black holes don't emit light. But we can see the stars orbiting it. Astronomers have been tracking those stars for decades, watching them whip around an invisible point at the center of the galaxy at speeds that reach a significant fraction of the speed of light. The orbits are so tight, so fast, that the only possible explanation is a black hole. A massive, compact object with enough gravity to sling stars around like they're nothing. In 2020, A team of astronomers used radio telescopes around the world to image the event horizon of Sagittarius A star directly. Not the black hole itself, but the shadow it casts against the glowing gas falling into it. The image was blurry, as expected. Radio telescopes don't have the resolution of optical telescopes, but it was there, a dark circle surrounded by a ring of light. Proof that the black hole is real. Sagittarius A star is quiet. It's not actively feeding. Not much gas is falling into it right now, but that hasn't always been the case. There's evidence that the Milky Way's central black hole was much more active in the past. And when supermassive black holes are actively feeding, they become some of the brightest objects in the universe. The gas falling toward a black hole doesn't fall straight in, it spirals. It forms an accretion disk, a swirling maelstrom of superheated gas orbiting the black hole at relativistic speeds. The friction in the disk heats the gas to millions of degrees. That hot gas radiates across the entire electromagnetic spectrum. X-rays, ultraviolet, visible light, infrared. In the most extreme cases, called quasars, the accretion disk around a supermassive black hole can outshine the entire galaxy surrounding it. Quasars are the most luminous active galaxies. They can radiate thousands of times more energy than a galaxy like the Milky Way, and all of that energy is coming from a region smaller than the solar system. A supermassive black hole feeding on a continuous stream of gas is one of the most efficient energy generators in the universe. More efficient than any star, more efficient than any supernova. About 10% of known galaxies are active, meaning their centers are more than 100 times brighter than the combined light of all their stars. That's a minority, sure, but it's a significant one. And it suggests that most galaxies, including the Milky Way, probably go through active phases, periods when the central black hole wakes up, starts feeding, and floods the galaxy with radiation. That radiation has consequences. The energy output from an active galactic nucleus, or AGN, can heat the surrounding gas so much that it can't collapse to form stars. This is called AGN feedback, and it's one of the main mechanisms that regulates star formation in massive galaxies. Without AGN feedback, the gas in large galaxies would cool too quickly and collapse into stars far faster than we observe. Galaxies would burn through their fuel in a fraction of the time and go dark. But the black hole prevents that. It heats the gas, keeps it buoyant, slows down the cooling. The galaxy forms stars at a steady, sustainable rate instead of burning everything at once. Supermassive black holes aren't just passengers sitting at the center of galaxies. They're active participants in galactic evolution. They shape the galaxies around them. They control how much gas is available for star formation. They regulate the growth of the galaxy itself, and they grow along with the galaxy, fed by the same gas that forms stars, locked in a feedback loop that ties the mass of the black hole to the mass of the surrounding bulge. The relationship is so tight that astronomers can predict the mass of a galaxy's central black hole just by measuring the mass of its bulge. Bigger bulge, bigger black hole. The two grow together. Galaxy mergers complicate everything. When two galaxies collide, their supermassive black holes eventually sink to the center of the merged system and spiral inward toward each other. The process takes a long time, hundreds of millions of years. But eventually, the two black holes get close enough that they merge, releasing a burst of gravitational waves so powerful it sends ripples through space-time itself. We haven't detected gravitational waves from merging supermassive black holes yet. The signal is too low frequency for current detectors, but future observatories, space-based gravitational wave detectors, should be able to pick them up. And when they do, we'll be able to watch black holes merge in real time, tracking the process from the first spiraling inward to the final collision. Mergers also trigger starbursts. When the gas clouds in two galaxies collide, they compress. Compressed gas forms stars, a lot of stars. Merger-driven starbursts can produce stars at rates hundreds of times faster than normal. For a few 100 million years, the merging system blazes with the light of billions of newborn stars. Then the gas runs out, the starburst fades, and what's left is a big, red, gas-poor elliptical galaxy with a supermassive black hole at its center, and not much else. Galaxy mergers are one of the main drivers of morphological change in the universe. Spirals become ellipticals. Small galaxies get absorbed by large ones. Structure is constantly being rearranged, and over billions of years, the overall trend is toward larger, redder, more passive galaxies. The universe is aging. Star formation rates across the cosmos have been declining for the past 10 billion years. Galaxies are running out of fuel. Between the stars, filling the space that looks empty but isn't, sits the interstellar medium, gas and dust and cosmic rays. The interstellar medium is the raw material from which stars form and the repository for the debris stars leave behind when they die. Most of the interstellar medium is hydrogen, about 90% by mass. Another 9% is helium. The remaining 1% is everything else: carbon, oxygen, nitrogen, all the heavy elements that stars and supernovae have created over billions of years. The interstellar medium is not uniformly distributed. It clumps. Some regions are dense, cold and dark. Molecular clouds where hydrogen has bonded into H2 molecules and mixed with dust grains. These are the star-forming regions, the places where gravity is winning and gas is collapsing into new stars. Other regions are hot and diffuse, ionized by radiation from nearby stars or heated by supernova shocks. The interstellar medium is a patchwork, a chaotic, turbulent, constantly churning mix of gas and dust and radiation. And it's cycling. Gas collapses into stars. Stars fuse hydrogen into helium and heavier elements. Massive stars explode and return enriched gas to the interstellar medium. That enriched gas mixes with pristine hydrogen falling into the galaxy from outside. New stars form from the mixture. The cycle repeats. Every generation of stars is slightly richer in heavy elements than the last. The Sun, a middle-aged star, contains about 2% heavy elements by mass. The first stars, the ones that formed a few 100 million years after the Big Bang, contained almost none, just hydrogen and helium. The universe has been enriching itself over time, building up the periodic table one supernova at a time. The interstellar medium matters for life, because planets don't form from pure hydrogen and helium. You need heavy elements: carbon for organic molecules, oxygen for water, silicon and iron for rocks and metal cores. Every element heavier than helium in your body, in the ground beneath your feet, in the air you breathe, was created inside a star or in a supernova explosion. We are, quite literally, made of stardust. Carl Sagan said it first, and it's become a cliché, but that doesn't make it less true. Every atom in your body, except for the hydrogen, was forged in the heart of a star billions of years ago. That star lived, burned and died, returning its enriched ashes to the interstellar medium. The Sun and the solar system formed from a cloud of gas that contained the debris of countless earlier generations of stars. And if you trace the history back far enough, every atom you're made of came from a galaxy, from the interstellar medium of some ancient spiral or dwarf galaxy that contributed its material to the cosmic web and eventually to us. Not every part of a galaxy is equally hospitable to life. The center, for instance, is a bad place to be. Radiation from the supermassive black hole, when it's active, would sterilize any nearby planets. The density of stars near the galactic core is so high that close encounters would be common. A passing star could destabilize a planetary system, flinging planets into interstellar space or sending them crashing into their sun. Supernovae near the galactic center are frequent. The radiation from a nearby supernova would strip away a planet's atmosphere and bathe the surface in lethal doses of gamma rays and cosmic rays. Life, if it exists, probably doesn't thrive there. The outer regions of a galaxy have the opposite problem. Too few heavy elements. Stars in the outer halo and the far edges of the disk are metal poor, meaning they formed from gas that hadn't been enriched much by earlier generations of stars. Planets around those stars, if they exist, would be small, low mass, composed mostly of hydrogen and helium. Rocky planets like Earth require heavy elements, and there aren't enough of them in the outer galaxy. The sweet spot, the region where conditions are most favorable, is called the galactic habitable zone. It's the region where there are enough heavy elements to form rocky planets, but not so much stellar density or radiation that life gets sterilized before it has a chance to start. The Sun sits comfortably in the galactic habitable zone, about halfway out from the center, in a quiet neighborhood between spiral arms, far from the chaos of the core, but enriched enough to have formed a rocky planet with liquid water. That might not be a coincidence. It might be selection bias. Life arose here because this is one of the places where life could arise. Galaxies with different structures, different chemical enrichment histories, different radiation environments might have very different habitable zones, or none at all. Our galaxy, the Milky Way, is not unique. It's large, sure, one of the bigger spirals in the local group of galaxies. But it's not extraordinary. There are billions of galaxies similar to the Milky Way scattered across the observable universe. Some larger, some smaller, all with their own histories, their own populations of stars, their own central black holes, their own interstellar media cycling gas and dust and heavy elements through generations of creation and destruction. The Milky Way is home, but it's just one home among trillions. One thread in the cosmic web, one island in an ocean so vast that light takes billions of years to cross it. And yet, for all its ordinariness, the Milky Way contains everything we know, every human who has ever lived, every civilization, every story, every discovery, every thought. It's all happened here, in this one galaxy, on one planet, orbiting one star, in one spiral arm. The rest of the Milky Way is out there, mostly unexplored, full of stars we've never visited, planets we've never seen, and possibly, just possibly, other forms of life we've never imagined. The galaxy is enormous. Even at the speed of light, it would take 100,000 years to cross from one side to the other. At the speeds we can currently achieve with spacecraft, it would take hundreds of millions of years. We're not leaving this galaxy, not anytime soon, not in any time frame that matters to human civilization. The Milky Way is our cage and our kingdom. Everything we'll ever touch, everything we'll ever explore, everything we'll ever know directly is here. The other galaxies, those 2 trillion islands scattered across the universe, are beyond our reach. We can see them, we can study them, we can count them and measure them and model them, but we will never visit them. The distances are too great. The universe is expanding too fast. The galaxies beyond our local group are already receding faster than we could ever chase them, and that recession is accelerating. We're stuck. Not on Earth, necessarily. With enough effort, we could spread through the solar system, maybe even to nearby stars. But the Milky Way is the limit, the boundary we can't cross. and that makes everything inside it matter more. The cradle of stars, that's what a galaxy is. A place where hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and oxygen becomes everything else. A place where gas collapses, stars ignite, planets form, and, at least in one case we know of, life begins. Galaxies are engines of complexity. They take the simplest possible ingredients, hydrogen and helium left over from the Big Bang, and they build structure. Stars, planets, molecules, chemistry, biology, consciousness. The process takes billions of years, and it's messy, violent, chaotic, and beautiful. Stars are born in clouds of gas and dust. They live, they burn, they die. Some fade quietly, shedding their outer layers into space and leaving behind white dwarfs. Others explode, scattering their guts across light years and triggering new waves of star formation in the debris. Black holes lurk at the centers, feeding when they can, regulating the growth of the galaxies around them. Gas flows in, stars form, gas flows out, the cycle continues. And all of this, every star, every planet, every black hole, every supernova, every molecular cloud, is happening simultaneously in 2 trillion galaxies scattered across the observable universe. The scale is incomprehensible, but the processes are universal. What's happening in the Milky Way is happening everywhere. The same physics, the same chemistry, the same story told 2 trillion times with local variations. And yet, with all we've learned about galaxies, with all the deep fields and all the surveys and all the simulations, there's something we still can't see, something hiding just beyond the reach of our instruments. Because the galaxies we count, the 2 trillion islands of light scattered across the universe, they're not everything. They're not even most of it. Most of the universe, as we've established, is invisible. Dark matter holding galaxies together. Dark energy tearing the universe apart. But there's something else, something we haven't accounted for. Light that never reaches us. Galaxies beyond the horizon. Structures hidden by dust or distance or the limits of our telescopes. The universe we can see, vast as it is just a fraction of what's out there. And that invisible universe, that unseen realm, is where the story goes next. We've spent this entire video looking at galaxies, counting them, mapping them, tracing their light back through billions of years of cosmic history. We've found 2 trillion of them scattered across the observable universe, each one a separate island containing hundreds of billions of stars. We've watched them cluster into groups, weave themselves into filaments, organize into a cosmic web that stretches across 500 million light-years. We've zoomed into the heart of a galaxy and seen stars being born, black holes feeding, gas cycling through generations of creation and destruction. The scale has been overwhelming. The numbers have long since stopped making sense. 2 trillion galaxies, each one containing billions or trillions of stars, each star potentially hosting planets. The sheer volume of stuff out there, the raw abundance of matter and light and structure, should be enough to fill any curiosity. It isn't. Because for all the galaxies we've counted, for all the deep fields we've taken, for all the light we've collected from the edges of space and time, there's something we haven't talked about yet. The boundary, the limit. The place where our observations stop, not because there's nothing beyond them, but because we've run out of universe we can see. There is an edge. Not an edge in space, not a wall you could fly to and touch, but an edge in knowledge, a horizon beyond which light has not had time to reach us. And on the other side of that horizon, invisible to every telescope we've ever built or ever will build, sits the rest of reality, the unseen universe. and it is almost certainly larger than everything we've talked about so far. The observable universe has a radius, 46.5 billion light-years. That's the distance to the farthest objects whose light has had time to reach Earth since the Big Bang. Notice the number, 46.5 billion light-years. The universe is only 13.8 billion years old. You'd think the observable radius would be 13.8 billion light-years, the distance light could travel in the time since the beginning. It's not. It's more than 3 times larger. And the reason has nothing to do with light breaking the speed limit. It's because space itself has been expanding while the light was traveling. Think of it this way. Imagine a photon leaving a distant galaxy shortly after the Big Bang. It starts moving toward us at the speed of light. But while it's traveling, the space between that galaxy and us is stretching. The galaxy is being carried away by the expansion of the universe. The photon is still moving toward us, but the finish line keeps moving farther away. The photon has to cover more ground than it would if space were static. It's like running on a treadmill that's speeding up. You're moving forward, but the belt is pulling backward, and you have to work harder to reach the front. Eventually, if the photon persists long enough, it crosses the expanding space and reaches us. By the time it arrives, the object that emitted it is no longer where it was when the photon left. It's been carried much farther away by the expansion. The light we're receiving today from the most distant galaxies left those galaxies when they were only a few billion light-years away. But in the time it took that light to reach us, the galaxies have been pushed out to 46.5 billion light-years. That's why the observable universe is so much larger than its age suggests. Space has been expanding the whole time. That radius, 46.5 billion light-years, defines something called the particle horizon. It's the boundary of everything we can observe right now. Everything whose light or other signals have had time to reach us since the beginning. Beyond that horizon, there are galaxies. Billions of them, maybe trillions. We know they're there because there's no reason to think the universe just stops at the edge of what we can see. The cosmic microwave background, the faint afterglow of the Big Bang, looks almost perfectly uniform in every direction. The temperature varies by less than 1 part in 100,000 across the entire sky. That uniformity tells us the early universe was smooth. The same conditions everywhere, the same density, the same temperature, the same laws of physics. If the universe were small, if it stopped just past our horizon, you'd expect to see some kind of edge effect, some asymmetry in the cosmic microwave background, some sign that one direction is different from another. We don't see that. The sky looks the same in every direction, which strongly suggests that the universe extends far beyond the particle horizon. The part we can see is just a bubble, a sample. And the rest of the universe, the part beyond the horizon, is more of the same. More galaxies, more stars, more structure, stretching out in every direction farther than we can measure. How much farther? That's where things get speculative. If the universe is infinite, which some models allow, then the observable universe is an infinitely small fraction of the total, an infinitesimal speck in an endless expanse. If the universe is finite but very large, the estimates vary wildly depending on the model. One calculation based on the flatness of space suggests the full universe is at least 250 times larger in radius than the observable part. That's a conservative lower bound. Other models, depending on assumptions about the shape of space and the specifics of cosmic inflation, push the number much higher. Some estimates suggest the total universe could be 10 to the power of 23 times larger than what we can see. That's not a typo. 10 to the power of 23, a 1 followed by 23 zeros. If that's true, the observable universe, with its 2 trillion galaxies, is a grain of sand on a beach that stretches across a continent, and we'll never see the rest of the beach. We can't. The light from those regions will never reach us, not because it's blocked, but because the universe is expanding too fast. The space between us and those distant regions is growing faster than light can cross it. The photons are still trying, still moving toward us at the speed of light, but they're losing ground. The expansion is winning. And as long as dark energy keeps accelerating the expansion, which all current observations suggest it will, those regions will remain forever out of reach. Not just technologically out of reach, fundamentally, physically, cosmologically out of reach. There's another horizon, a different kind. The cosmic event horizon. This one doesn't mark the edge of what we can see now. It marks the edge of what we'll ever be able to see in the future. If you emit a photon from Earth today, how far can it travel before the expansion of space carries distant regions away faster than the photon can reach them? The answer, in the standard model with a cosmological constant, is about 18 billion light-years. That's the event horizon. Any galaxy sitting beyond 18 billion light-years from us right now will never receive light we emit today, and symmetrically, any light those galaxies emit today will never reach us. The event horizon is shrinking, not in distance, but in scope. As the universe expands and dark energy dominates, the volume of space we can communicate with, the region within our event horizon, is getting smaller relative to the total universe. Galaxies that are currently just inside our event horizon will eventually cross it and vanish from our future. Not because they're destroyed, because the space between us and them expands faster than light. They'll still exist. They'll still be shining, but their light will never reach us again. They'll slip over the horizon and disappear, not into nothingness, but into a part of the universe we can no longer access. This is the ultimate isolation. In a universe dominated by dark energy, every galaxy cluster that isn't gravitationally bound to us will eventually recede beyond the cosmic event horizon. Billions of years from now, if there are still astronomers on Earth or anywhere in our local group of galaxies, they'll look up at the sky and see almost nothing. The Milky Way, Andromeda, the other members of the local group, all still bound together by gravity. But beyond that, darkness. The cosmic web will be gone. The distant galaxy clusters will have vanished. The cosmic microwave background will have redshifted so far into the infrared, then into the radio, then beyond, that it will be undetectable. Future civilizations, if they exist, will have no observational evidence that the universe is larger than the local group. They'll see a small collection of galaxies surrounded by emptiness. And unless we leave them records, unless we somehow preserve the knowledge we've gained in this brief window of cosmic history, when the rest of the universe is still visible, they'll have no way to know what we know. That the universe is vast, that it's expanding, that it was once filled with light and structure stretching in every direction. The cosmic horizon is closing, slowly but inevitably. And on cosmological timescales, we're living in a golden age. The age when the universe is old enough to have formed galaxies and stars and planets and life, but young enough that we can still see the full scope of creation. That window won't stay open forever. What lies beyond the horizon? We can't know for certain, but the simplest assumption, and the one most cosmologists accept, is that it's more of the same. More galaxies, more clusters, more filaments and voids, the same laws of physics, the same kinds of stars and planets and black holes. But there are other possibilities, speculative possibilities that push into the territory of hypothesis rather than observation. One of the most talked about is the multiverse. The idea that our universe, the region within our particle horizon, is just one bubble in a much larger structure, that the Big Bang wasn't the beginning of everything, just the beginning of our local patch of space, and that beyond our horizon there could be other patches, other universes with their own Big Bangs, their own histories, their own laws of physics. Some versions of the multiverse come from cosmic inflation, the theory that the early universe expanded exponentially in the first fraction of a second after the Big Bang. Inflation explains why the universe is so flat and uniform, but it also predicts that inflation didn't happen everywhere at once. Different regions of space could stop inflating at different times, and each region that stops becomes a separate universe, a bubble with its own particle horizon, its own galaxies, its own set of physical constants. If inflation is eternal, if it keeps happening forever in some regions while stopping in others, then the multiverse is infinite. An endless sea of bubble universes, each one isolated from the others by horizons that can never be crossed. In some of those universes, the laws of physics might be different. The strength of gravity might be weaker or stronger. The mass of the electron might be different. The cosmological constant might be larger or smaller. Most of those universes would be sterile, incapable of forming stars or galaxies or anything interesting, but a few, a tiny fraction, would have conditions similar to ours, conditions that allow complexity, stars, planets, chemistry, life. We happen to live in one of those rare universes, not because we're special, but because we couldn't exist anywhere else. That's the anthropic principle. The multiverse doesn't care about us. It's not designed for us. It's just so large and so varied that somewhere, by pure chance, conditions align to allow life. And we're here because this is where here is possible. It's a deeply unsatisfying answer to the question of why the universe looks the way it does, but it's not obviously wrong. The problem is that it's not testable. If the other universes are beyond our cosmic horizon, we can't observe them, we can't measure them, we can't confirm or rule out their existence. The multiverse is a hypothesis that might be true, but it exists in a space where science struggles. The space of ideas that make sense mathematically but can't be checked against observation. Some physicists embrace the multiverse as the best explanation for why our universe's physical constants seem fine-tuned for life. Others reject it as untestable metaphysics. The debate is ongoing. What about life beyond Earth? Not beyond our universe, but within it, within the 2 trillion galaxies we can see. The question isn't whether life exists elsewhere. The question is whether we can find it. The numbers suggest we're not alone. 2 trillion galaxies, hundreds of billions of stars in each one. A significant fraction of those stars have planets. We know this because we've found thousands of exoplanets around nearby stars, and the detection methods we're using are biased toward finding large planets close to their stars. Small rocky planets in the habitable zone, the region where liquid water can exist, are harder to detect but appear to be common. Estimates suggest there are tens of billions of habitable zone planets in the Milky Way alone. Multiply that by 2 trillion galaxies, and the number of potentially habitable planets in the observable universe is staggering. If life is even remotely common, if the emergence of biology isn't an absurdly rare fluke, then the universe should be teeming with it. Maybe not intelligent life, maybe not technological civilizations, but life, microbes, ecosystems, something. The search for extraterrestrial intelligence, SETI, has been scanning the skies for decades, looking for radio signals that could only come from an advanced civilization. So far, nothing. The silence is deafening. There are explanations. Maybe intelligent life is rare. Maybe civilizations don't last long. Maybe they destroy themselves shortly after developing the technology to send signals across space. Maybe they lose interest in communicating. Maybe they're using communication methods we haven't thought of, and we're listening on the wrong channel. Or maybe the distances are just too vast. Even if there are millions of intelligent civilizations in the Milky Way, the galaxy is 100,000 light-years across. If the nearest civilization is 1,000 light-years away, which is close by galactic standards, any signal they sent 1,000 years ago is just now reaching us, and if we reply, it'll take another 1,000 years for our signal to reach them, 2,000 years round trip. Civilizations rise and fall in less time than that. Interstellar conversation isn't practical, it's not impossible, but it's slow. Painfully slow, and if the nearest civilization is 10,000 light-years away or 100,000, the conversation becomes meaningless. You're talking to ghosts, sending messages to civilizations that might not exist anymore, and receiving replies that were sent before your own civilization was born. And that's just within our galaxy. If you want to think about life in other galaxies, the problem gets worse. The nearest large galaxy, Andromeda, is 2.5 million light-years away. Any signal from Andromeda left before humans existed, before our genus existed, before most of the species we recognize as human ancestors had evolved. If someone in Andromeda is trying to contact us, we won't hear from them for another 2.5 million years. And if we reply, they won't get our message for another 2.5 million years after that. 5 million years round trip. That's not communication, that's archaeology. Beyond Andromeda, the distances only grow. Galaxies billions of light-years away, the ones we see in the deep fields, are so far that any signal from them would take longer to reach us than the current age of the Earth. If there were civilizations in those galaxies when the light we're seeing left them, and if they sent signals toward us at the same time, those signals are still in transit, and by the time they arrive, if they ever do, the civilizations that sent them will be gone, dead, extinct, evolved into something unrecognizable, or the galaxies themselves will have changed so much that the original context no longer exists. The universe is too big, the speed of light is too slow, the distances are too great. We're isolated not by space, but by time, by the simple fact that the universe is so large that information takes billions of years to cross it, and in those billions of years, everything changes. The horizon problem extends to signals. The same cosmic event horizon that limits how far light can travel also limits how far any signal, electromagnetic or otherwise, can reach. If a civilization exists beyond our event horizon, we'll never hear from them. Their signals will never reach us. Not because they're too faint, because the space between us is expanding too fast. The signal is chasing us, but it's losing ground. And we're chasing them, but we'll never catch up. The horizon ensures that most of the universe, most of the galaxies, most of the potential civilizations that might exist out there are unreachable. We can see some of them, the ones close enough that their light has had time to reach us. But we can't communicate with them, we can't visit them. We can't learn anything about them except what their ancient light reveals. And for the galaxies beyond the horizon, we can't even do that. They exist, almost certainly, but they're gone. Not destroyed, just unreachable, beyond the veil, and they'll stay there forever. Technological limitations make things worse. Even within the observable universe, we're struggling to see clearly. The James Webb Space Telescope is the most powerful observatory we've ever built, and it's showing us galaxies from the first few 100 million years after the Big Bang, but it's still missing most of them. The faintest galaxies, the smallest ones, the ones sitting just below the detection threshold, remain invisible. We know they're there because the models predict them, because the cosmic background light suggests their presence, but we can't resolve them individually. And beyond a certain distance, even Webb hits a wall, not a physical wall, a practical one. The redshift becomes so extreme that the light is stretched into wavelengths no current detector can pick up. The cosmic microwave background, that faint glow of radiation left over from the Big Bang, sits at a redshift of about 1000. Any galaxy sitting beyond that, any structure that formed before the universe cooled enough to become transparent, is hidden behind an opaque wall of radiation. We can't see past it, not with light. The universe before that moment is invisible to telescopes, permanently. That's the surface of last scattering, the place where photons last interacted with matter before streaming freely through space. It's the ultimate horizon for electromagnetic observations. Beyond it, the universe was opaque, a hot, dense fog. No stars, no galaxies, just plasma. And we can't see into plasma. The photons scatter. They don't travel in straight lines. They don't carry images. The cosmic microwave background is the earliest light we'll ever detect. Everything before that is dark. But there are other ways to probe the early universe. Gravitational waves. These are ripples in space-time itself, caused by the acceleration of massive objects. Black holes merging. Neutron stars colliding. In principle, violent events in the very early universe, perhaps even the end of cosmic inflation itself. Gravitational waves don't interact with matter the way light does. They pass through everything. They're not absorbed or scattered by the fog of the early universe, which means gravitational waves could carry information from before the surface of last scattering, from moments so early that the universe was only fractions of a second old. Detecting those waves is extraordinarily difficult. Current detectors like LIGO can pick up gravitational waves from merging black holes and neutron stars, events that produce strong signals at frequencies LIGO is designed to hear. But the gravitational waves from the early universe would be much weaker and at much lower frequencies. Detecting them will require new instruments, space-based detectors, observatories that can measure the stretching and compressing of space-time over distances of millions of kilometers. Those projects are being designed. They're decades away from launch, but if they work, they'll open a new window, a way to see the universe not with light, but with gravity, a way to probe the unseen. The other major unseen is the nature of reality itself. Dark matter and dark energy dominate the universe, but we don't know what they are. We've built the standard model of cosmology, and it works. It fits the data. It makes predictions that hold up under observation. But it rests on two pillars we don't understand. Dark matter is invisible. Dark energy is unexplained. Together they make up 95% of everything. And we can't put either one in a lab. The search for a theory that unifies gravity and quantum mechanics, the so-called theory of everything, is ongoing. General relativity describes gravity beautifully on large scales. Galaxies, clusters, the expansion of the universe. Quantum mechanics describes the behavior of particles and forces on small scales. Atoms, photons, the inner workings of stars. But the two theories don't fit together. They use different mathematics, different assumptions, different pictures of reality. And at the places where they should overlap, in the centers of black holes, in the first moments of the Big Bang, they give contradictory answers. Physicists have been trying to reconcile them for nearly a century. No one has succeeded. String theory, loop quantum gravity, and a dozen other approaches have been proposed. None have been confirmed. The universe operates according to rules we don't fully understand, and until we find the theory that unifies gravity and quantum mechanics, There will be questions we can't answer, places in the cosmos where our models break down and we're left guessing. The philosophical weight of all this is hard to overstate. We've mapped 2 trillion galaxies. We've traced the cosmic web across 500 million light-years. We've watched stars being born, and black holes feeding, and gas cycling through generations of creation and destruction. We've built a cosmological model that describes the universe from the first fraction of a second after the Big Bang to the present day, and yet 95% of the universe is invisible. Most of the galaxies that exist are beyond our horizon. The laws of physics that govern reality at its deepest levels remain elusive. The multiverse may or may not exist, and we have no way to check. The possibility of life elsewhere in the cosmos seems overwhelming, but the distances ensure we'll almost certainly never meet. And the future of the universe, if dark energy stays constant, is a slow fade into darkness as galaxies slip over the horizon one by one until nothing remains but our local cluster surrounded by emptiness. We're living in a golden age. The age when the universe is old enough to understand but young enough to see. That age won't last. Cosmologically speaking, it's already ending. The galaxies are receding. The horizon is closing, and future civilizations, if they exist, will look up at a sky that's almost empty and wonder if they're alone. But for now, right now, in this brief window of cosmic time, we can see, we can count the galaxies, we can trace the light back billions of years. We can map the structure of the universe on the largest scales imaginable. We can ask questions about where we came from, what the universe is made of, where it's going. And we can glimpse, just barely, the edge of the veil, the boundary of knowledge, the place where observation stops and speculation begins. Beyond that veil sits the rest of the universe, the unseen cosmos, larger, stranger, more varied than anything we've described, and we'll never see it. We can infer it, model it, imagine it, but we can't observe it. The horizon is absolute, the speed of light is finite, the universe is expanding, and most of reality, the vast majority of existence, is and will always remain invisible. That's not a failure of technology. It's not something better telescopes will fix. It's a fundamental limit built into the structure of space-time itself. The universe has edges. Not edges in space, but edges in knowledge. And beyond those edges, the unseen universe stretches on, full of galaxies we'll never count, stars we'll never see, planets we'll never visit, and possibly life we'll never meet. It's out there, somewhere, beyond the veil, and it's bigger than everything we know. We've covered a lot of ground, 13.8 billion years of cosmic history compressed into a single video. We started with Edwin Hubble in 1923, standing in front of a photographic plate, staring at individual stars in what everyone thought was just another nebula inside our own galaxy. That single observation shattered the accepted view of the universe. Andromeda wasn't part of the Milky Way. It was an entirely separate galaxy, sitting more than 2 million light-years away. And if Andromeda was out there, then so were all the other spiral nebulae. The universe wasn't a single island, it was an ocean. From there, we watched the count climb. Slowly at first, a few dozen galaxies, then a few hundred, then thousands, as surveys got deeper and telescopes got better. The Hubble Deep Field in 1996 showed 3,000 galaxies in a patch of sky smaller than a grain of sand held at arm's length. The ultra-deep field pushed that to 10,000. Each new observation revealed more structure, more depth, more galaxies hiding in the spaces we thought were empty. The estimates kept rising. 70 billion galaxies, 100 billion, 200 billion. Then, in 2016, Christopher Consolice's team revised the number upward by a factor of 10, 2 trillion galaxies. Not because we suddenly saw 10 times more galaxies in the images, because we realized how many we were missing, how many faint, small, distant galaxies were sitting below the detection threshold, invisible to Hubble but undeniably there. The models predicted them. The cosmic background light confirmed them. And when the James Webb Space Telescope came online and started finding galaxies at redshifts Hubble couldn't reach, the predictions held up. The universe kept delivering more galaxies, always more. The current working estimate sits somewhere between 2 trillion and 6 trillion, depending on whose model you trust and how you account for the galaxies we still can't see. 6 trillion. That's the high end. 6 million separate islands of stars scattered across the observable universe. And that's just what we can see, the part within our cosmic horizon. Beyond that horizon, unreachable and unobservable, sits the rest, the unseen universe, possibly infinite. At minimum, hundreds of times larger than the bubble we can observe. Most of reality is invisible, not because it's dark, because it's too far away. The light hasn't had time to reach us, and with dark energy accelerating the expansion, it never will. So here we are, standing on a planet that's 4.5 billion years old, orbiting a star that's middle-aged and unremarkable, in a galaxy that contains somewhere between 200 billion and 400 billion other stars. And that galaxy is one of up to 6 trillion in the observable universe alone. The scale is so large, it stops meaning anything. Your brain can't hold 6 trillion galaxies. It can't visualize 100 billion stars in a single galaxy. The numbers are too big. They're abstractions. But the implications aren't abstract. They're immediate and personal and deeply uncomfortable. Because if the universe contains 6 trillion galaxies, and if each galaxy contains hundreds of billions of stars, and if a significant fraction of those stars have planets, and if even a tiny percentage of those planets are capable of supporting life, then the odds that Earth is the only place where life has ever emerged become vanishingly small, statistically negligible, absurd even. And yet, we have no evidence of life anywhere else. Not a single confirmed biosignature, not a single radio signal that couldn't be explained by natural processes, not a single probe, artifact, or visitor from beyond. The silence is total, which means one of two things. Either life is so rare, so improbable, that it only happened once in 6 trillion galaxies, or it's common, and we're just not looking in the right places, or not looking in the right way, or we're too far apart in space or time to ever make contact. Both possibilities are unsettling. The first makes us cosmically unique, but also cosmically alone. The last survivors of a process so unlikely it borders on miraculous. The second makes us cosmically typical, but still isolated. One voice in a choir so vast that no one can hear anyone else over the distance. Either way, we're stuck here, on this planet, in this solar system, in this galaxy. The distances between stars are measured in light years. The distances between galaxies in millions or billions of light years. We're not crossing those gaps. Not with any technology we currently have or can reasonably imagine developing in the next few centuries. The speed of light is a hard limit, and even if we could travel at light speed, which we can't, it would take 2.5 million years to reach Andromeda. 100,000 years just to cross our own galaxy. The universe is too big, we're too slow, and the expansion is making it worse. Every day, the galaxies beyond our local group are a little farther away. Every year, a few more galaxies slip over the cosmic event horizon and disappear from our future. The universe we can see is shrinking. not in absolute size, in accessibility. Billions of years from now, if there are still astronomers looking up from Earth or anywhere in the local group, they'll see almost nothing. Just the Milky Way, Andromeda, and the few dozen smaller galaxies bound to them by gravity. The rest will be gone, not destroyed, just beyond reach. And unless we leave records, unless we preserve what we've learned in this brief window when the full scope of the universe is still visible, future civilizations will have no way to know what we know. They'll think the universe is small, local, empty beyond their immediate neighborhood. They'll be wrong, but they won't have any evidence to prove it. The cosmic microwave background will have redshifted into undetectability. The distant galaxies will have vanished. The expansion will have erased the view. We're living in the golden age, the time when the universe is old enough to have formed structure, stars, planets, life, intelligence, but young enough that we can still see the full picture. That won't last. Cosmologically speaking, we're already near the end of it. Carl Sagan called Earth a pale blue dot. He was looking at a photograph taken by Voyager 1 in 1990, a picture of Earth from 6 billion kilometers away, just past the orbit of Neptune. In that image, Earth is less than a single pixel, a tiny speck of light suspended in a shaft of scattered sunlight. Sagan wrote about it in a way that's been quoted so often it's become a cliché, but the words still hit. Everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was, lived out their lives on that dot. Every hero and coward, every creator and destroyer of civilization, every king and peasant, every couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That's the view from 6 billion kilometers. The view from 6 trillion galaxies is incomparably smaller. Earth isn't even a pixel from that distance. It's invisible, undetectable. A planet orbiting a star that's one of hundreds of billions in a galaxy that's one of trillions. From the perspective of the universe, we don't register. We're a rounding error. Less than that, we're nothing. A brief flicker of chemistry on a rock that will be cold and dead in a few billion years, orbiting a star that will swell into a red giant and vaporize the planet long before the universe runs out of time. On a cosmic scale, we're insignificant, temporary, irrelevant, and yet, we're the only thing in the universe, as far as we know, that can comprehend the universe. The only structure complex enough and organized enough to look outward, measure distances, count galaxies, model the expansion of space, trace the history of the cosmos back to the first fraction of a second after the Big Bang. Stars don't do that. Galaxies don't do that. Black holes, for all their mass and power, don't know they exist. Humans do. We know we exist. We know the universe exists. We know how big it is, how old it is, what it's made of, where it came from, and where it's going. That knowledge didn't come from revelation. It came from centuries of careful observation, mathematical reasoning, technological innovation, and sheer stubborn curiosity. From people like Edwin Hubble pointing telescopes at fuzzy patches of light and refusing to accept that they were just nebula until the evidence proved otherwise. From people like Vera Rubin measuring galaxy rotation curves and realizing the mass didn't match the light, forcing the field to accept that most of the universe is invisible. From people like Adam Rees and his team measuring distant supernovae and discovering that the universe isn't just expanding, it's accelerating, driven by a force we still don't understand. from engineers and scientists who spent decades designing, building, and launching the Hubble Space Telescope, then fixing it when the mirror turned out to be ground wrong, then using it to stare at empty patches of sky for days at a time just to see what was there. From the teams that built the James Webb Space Telescope, the most complex observatory ever constructed, and sent it 1,000,000 miles from Earth to peer deeper into space and time than anyone thought possible. That's not insignificant. That's the opposite of insignificant. That's a species that looked up at the night sky and decided it needed to know what it was looking at, and then spent centuries figuring it out. The fact that we're small doesn't make us meaningless. It makes what we've accomplished more remarkable, because we did all of this from one planet, with brains that evolved to hunt animals and gather plants and avoid predators on the African savanna. Brains that have no evolutionary reason to be good at cosmology. And yet, we built telescopes, we wrote equations, we launched satellites. We imaged galaxies 13 billion light-years away, and measured their redshifts, and calculated their distances, and traced the structure of the universe across scales so vast that the human mind can't visualize them. We did that. Not gods, not aliens, not some advanced civilization with a billion-year head start. Us, humans, a species that's been doing science for maybe 400 years, depending on how you count, and has been looking at the deep universe with serious instruments for less than a century. And in that time, we went from thinking the Milky Way was the entire universe to knowing there are trillions of galaxies. That's not insignificance. That's the most significant thing any collection of atoms has ever done. The universe doesn't care about us. It's not hostile. It's not benevolent. It just is. A vast, expanding, mostly empty structure governed by physical laws that don't know we exist and wouldn't change if we disappeared tomorrow. But we care about the universe. We want to understand it. We want to know how it works, where it came from, what it's made of, whether we're alone in it. That curiosity is unique. As far as we can tell, it's the only thing in the cosmos asking these questions. And that matters, not to the universe, to us, because understanding the universe changes how we see ourselves. It changes what we think is possible. It changes what we value and what we're willing to work toward. When Edwin Hubble proved that Andromeda was a separate galaxy, he didn't just add a data point to astronomy. He expanded the human conception of reality. He showed that the universe was bigger than anyone imagined. When the Hubble Deep Field revealed thousands of galaxies in a patch of sky no one thought contained anything, it didn't just increase the galaxy count. It proved that the universe was full. That everywhere you looked, if you looked deep enough, you'd find more structure, more light, more worlds. When the James Webb Space Telescope started finding galaxies at redshifts so high they shouldn't exist according to the models, it didn't just create a problem for cosmologists. It showed that the universe is still capable of surprising us, that we don't have all the answers, that there are mysteries left, and that the only way to solve them is to keep looking. The tools are getting better. Webb is operational now, and it's going to keep observing for years. It's going to find fainter galaxies, push further back in time, resolve more detail in the structures we've already seen. But Webb isn't the endpoint, it's one step. The next generation of ground-based telescopes, the Extremely Large Telescope and the Giant Magellan Telescope, both under construction, will have mirrors so large they'll collect more light than any telescope ever built. They'll be able to image exoplanet atmospheres directly. They'll be able to study the chemical composition of distant galaxies in detail. They'll push the boundaries of what we can see from the ground. And beyond that, there are plans for space telescopes even more powerful than Webb. Observatories designed to study the cosmic microwave background in exquisite detail, to detect gravitational waves from the early universe, to map the distribution of dark matter across the entire sky. The roadmap is decades long, but the direction is clear. We're going deeper, further. We're not stopping. And the more we see, the more questions we uncover. Why did galaxies form so quickly in the early universe? Why are some of them so massive so soon after the Big Bang? What is dark matter made of? Why is dark energy's density so finely tuned? Is the cosmological constant really constant, or does it change over time? Why is the universe so flat? Why did inflation happen, and what stopped it? Are there other universes beyond our cosmic horizon? And if so, are their physical laws different from ours? Could we ever detect them? Could we ever prove the multiverse exists? Or is it destined to remain a beautiful idea with no observational test? We don't know. We might never know. Some of these questions might be unanswerable, not because we're not smart enough, because the answers lie beyond the edge of what's physically observable. But that doesn't mean we stop asking, because the process of asking, the process of pushing against the boundaries of knowledge, is what defines us. It's what makes us human in the deepest sense. We're the species that looks at the horizon and wonders what's on the other side. And when we reach the horizon and see further, we wonder what's beyond that. The curiosity is endless. The questions are inexhaustible, and that's good, because the universe is bigger than we'll ever fully comprehend, and we're going to spend the rest of our existence trying anyway. There are ethical dimensions to this too. If the universe contains trillions of galaxies, and if even a small fraction of the planets in those galaxies harbor life, then we have to think seriously about what contact would mean, not just for us, for them. We've spent decades beaming radio signals into space, announcing our presence to anyone who might be listening. We've sent probes carrying information about Earth, about humans, about where we are and what we're made of, out beyond the solar system. Voyager 1 and Voyager 2 are both in interstellar space now, carrying golden records with sounds and images from Earth. The idea was that if anyone ever found them, they'd know we were here, that we tried to reach out. But what if reaching out is dangerous? What if the universe is full of civilizations, and the reason we haven't heard from any of them is because the ones that broadcast their locations don't survive? What if silence is the optimal strategy, and we've been shouting into the void for 50 years? We don't know. We can't know. Not until we make contact, or fail to, or get a response we weren't expecting. The question of whether we should be trying to contact alien civilizations is one of the biggest unresolved debates in the scientific community. Some argue that the potential benefits, learning from a more advanced civilization, sharing knowledge, joining a galactic community, outweigh the risks. Others argue that we have no idea what we're dealing with, that broadcasting our presence could be inviting disaster, and that we should be listening instead of shouting. Both sides have reasonable points. And the decision, if we ever make it as a species rather than as a collection of individual researchers and organizations doing their own thing, will shape our future in ways we can't predict. Then there's the question of what we do with the knowledge we're gaining. Understanding the universe doesn't feed anyone. It doesn't cure diseases. It doesn't stop wars, and yet the technologies developed to study the cosmos have had enormous practical benefits. GPS relies on general relativity. Medical imaging uses principles developed in radio astronomy. The sensors in your phone descended from technology built for space telescopes. The process of trying to answer fundamental questions about reality often leads to tools and techniques that change everyday life in ways no one anticipated. That's not a justification. Science doesn't need to justify itself by producing gadgets. The pursuit of knowledge is valuable in its own right. But it's worth noting that the line between pure research and practical application is blurrier than most people think. Understanding the universe makes us better at manipulating the universe, and the better we get at that, the more capable we become of shaping our own future. Right now, we're living through a revolution. The James Webb Space Telescope has been operational for just over 2 years, and it's already rewriting textbooks. Every deep field it takes reveals structures we didn't predict, galaxies that shouldn't exist, stars forming faster than the models allow, black holes that grew too quickly. The universe is not behaving the way we thought it would. That's not a failure, that's an opportunity. Because every time the universe surprises us, we learn something. We refine the models, we build better theories, we ask sharper questions. The process is slow, frustrating, full of dead ends and false starts, but it works. And it's the only process we have that reliably produces knowledge about reality. You can't intuit your way to the age of the universe. You can't meditate your way to the mass of a black hole. You can't philosophize your way to the expansion rate of space. You have to measure. You have to build instruments. You have to gather data. You have to test hypotheses against observation and throw out the ones that don't fit, no matter how elegant they are, no matter how much you want them to be true. That's science. And it's the reason we know anything at all about the 6 trillion galaxies scattered across the observable universe. We're not going to visit those galaxies, not in any time frame that matters, but we're going to keep looking at them. We're going to keep counting them. We're going to keep measuring their properties, tracking their motions, modeling their evolution, searching for signs of life, trying to understand how they fit into the larger structure of reality. Because that's what we do. We're a curious species. Curious enough to spend billions of dollars and decades of effort to take pictures of objects so far away their light has been traveling since before Earth existed. Curious enough to stare at those pictures and ask why. Curious enough to build mathematical models of the entire universe and test them against tiny fluctuations in a background glow of radiation left over from the Big Bang. Curious enough to wonder, seriously and persistently, whether we're alone. And curious enough to keep searching even when the silence suggests we might be. The pale blue dot is still here, still orbiting the sun, still home to 8 billion humans and trillions of other living things. Still the only place in the universe we know for certain that life exists. It's small, cosmically insignificant, a speck in an ocean of 6 trillion islands, most of which we'll never see clearly, none of which we'll ever visit. But it's ours, and from this tiny vantage point, we've managed to map the ocean. We've counted the islands, we've traced the currents, we've measured the depth. We've looked back in time to watch the ocean form, and we've looked forward to see how it will end. We've done all of that from one planet, with telescopes we built, with equations we wrote, with minds that weren't designed for this but learnt how to do it anyway. That's not insignificance, that's triumph. The universe is vast. We are small, and we're the only part of the universe, as far as we know, that knows the universe is vast, that makes us matter, not to the cosmos, to each other, to the future, to whatever comes next. Because the story isn't over. We've mapped 6 trillion galaxies. There are more we haven't found yet, more beyond the horizon we'll never see, more questions than answers, more mysteries than solutions. And as long as there are humans, or whatever we become, looking up at the sky and asking why, the search will continue. The ocean of light is waiting. We're still exploring it, and we're nowhere near finished. So here we are. We started by asking how many galaxies exist and ended up somewhere much stranger. Not just with a number, though the number is staggering. 6 trillion galaxies in the observable universe, maybe more, each one containing hundreds of billions of stars, each star potentially hosting planets, each planet a world with its own history, its own geology, its own chance at complexity. The scale breaks language. It turns numbers into noise. But the scale isn't the point. The point is what we did to get here. We built telescopes. We launched them into space. We pointed them at patches of sky so empty that no one thought there was anything worth seeing. And we stared for days, for weeks. We collected photons that had been traveling for 13 billion years, light that left distant galaxies when the universe was still in its infancy. And we turned those photons into knowledge. We measured distances across cosmic time. We mapped structures 500 million light-years wide. We discovered that most of the universe is invisible, that space itself is expanding, that the galaxies we see today are just fossils, snapshots of objects that have already changed beyond recognition. We learnt all of that from one planet, with brains that evolved to hunt and gather, not to do cosmology. And yet here we are, holding a map of the observable universe in our heads, debating the nature of dark energy, counting galaxies we will never visit, asking whether we are alone in an ocean of 6 trillion islands. The universe does not care that we did this. It was not waiting to be understood. But we cared. We wanted to know. And that wanting, that relentless, stubborn refusal to accept ignorance, is the only thing in the cosmos that has ever looked back at itself and asked why. That is not insignificance. That is the opposite. We are small. The universe is vast. And somehow, against all odds, the small thing learned to measure the vast thing. That might be the most remarkable fact in all of cosmology. Not that the universe is large, that something inside it finally